Hello there, and welcome to the Cosmographer. In 1976, an experiment sitting on the surface of Mars returned a result that met its own published criteria for detecting biological activity at two landing sites 4,000 kilometers apart, and in the 50 years since, nobody has ever repeated it. That is number 9 on this list, and it is not the strangest entry on it. Number 18 is a group of mountains mistaken for monuments until someone measured the largest and found it 13 times taller than the Great Pyramid. Number 10 is a set of carbon chains pulled from a 12-year-old sample that had been sitting unused inside a rover, and they are the largest organic molecules ever found on another world. Number 4 is a reading of the Martian crust, suggesting there is more liquid water 12 kilometers beneath the ground than in all of Earth's rivers and lakes combined. 20 discoveries, ordered not by how alarming they sound, but by how much verified evidence sits behind each one, and the entry at the top of the list is the one nobody has ever tested. Get comfortable and settle in. If you enjoy falling asleep to lists that take the long way through the evidence, a quick like and subscribe helps this channel reach more curious minds like you. Because by the time we reach number 1, the question will have quietly changed shape. Let's begin at number 20. Number 20, the face at Cydonia. There are 20 entries on this list, and every one of them is a real observation. Each was made by a named instrument, on a named date, and every number attached to it was measured rather than imagined. That is the rule this list runs on, and it is worth stating at the beginning, because the question underneath the list is one that usually keeps poor company. The question is whether anything reached Mars before we did. Not whether anyone has claimed it, but whether the actual record, the photographs, the spectra, the drill cores, the seismic traces, contains anything that points that way. It turns out the honest version of that question is considerably more interesting than the sensational version, and it takes about 3 hours to walk through properly. The ordering is deliberate. These 20 entries are not ranked by how alarming they sound. They are ranked by how much verified evidence sits behind them. Number 20 is the most famous claim ever made about Mars and the one most thoroughly explained away. Number 1 has never been tested at all. So the descent runs from noise towards signal, and by the time we reach the end, the entries that were loudest at the start will look very small. We begin where almost everyone begins. On the 25th of July 1976, the Viking 1 orbiter was mapping a region called Cydonia Mensae. Cydonia sits at about 40 degrees north, in the transition zone between the cratered uplands of Western Arabia Terra and the low northern plains. It is a landscape of mesas, knobs and ridges, thousands of them, left behind as the ground between them eroded away. The orbiter photographed one of those mesas in frame 35A72 at a resolution of roughly 43 meters per pixel, with the sun low in the afternoon sky. The mesa is about 1.5 kilometers across. In that frame, under that light, it looked like a human face looking upward. The image was released with a caption noting the resemblance and attributing it to the play of shadow. The caption did not survive contact with the public. Within a few years, the photograph had become the single most reproduced image in the history of Martian speculation, and the argument built around it was genuinely careful in places. The feature was large. Its proportions looked symmetrical. There appeared to be a brow line, a nose, a mouth, and even what some described as a tear duct. 2 facts about that original image explain most of what followed. The first is resolution. 43 meters per pixel means that each individual dot in the picture covers a patch of ground roughly the size of a large house. Details being argued over, the shape of a nostril, the line of a lip, were being read from features smaller than the smallest thing the camera could actually see. The second fact is more specific. A single black speck near the center of the face was widely interpreted as a nostril. It was a data dropout, a place where a bit of information was lost during transmission from Mars to Earth, and there are similar specks scattered across the rest of the frame where nobody was looking. The resolution to the argument arrived in 3 stages, and each one is a matter of public record. There is also a second Viking image of the same ground, catalogued as frame 70A13, taken on a later orbit at a different sun angle. In that one, the face is already much harder to see, because the shadows fall differently, and the western flank reads as what it is, a slope. That frame was available from the beginning. It was simply never the one that circulated. The camera that eventually settled the question has a history of its own worth a moment. It was built by a small company founded by the geologist who had proposed it, and an earlier version of the same instrument had already been lost once. It was aboard Mars Observer, which fell silent on the 21st of August, 1993, 3 days before it was due to enter orbit, and was never heard from again. The camera that finally photographed Cydonia properly was the second attempt at flying the same idea. On the 5th of April 1998, the Mars Orbiter camera aboard Mars Global Surveyor imaged Cydonia at about 4.5 meters per pixel, roughly 10 times sharper than Viking. The mesa lost most of its face. Some argued the image had been processed unfairly, so the raw frame was released alongside the enhanced version. On the 8th of April 2001, the same camera imaged the same mesa again, this time from an altitude of about 450 kilometers, in cloudless conditions, with the sun high enough to flatten the shadows that had done so much of the original work. That image resolves the ground at roughly 1.5 meters per pixel. At that scale, you could see a parked car. There is no face. In 2006, the high-resolution stereo camera aboard Mars Express photographed the whole Cydonia group in stereo and produced a 3-dimensional elevation model. That was the final step, because a model measures the shape rather than inferring it from light. What the model shows is an eroded mesa with a collapsed western flank, roughly 240 meters above the surrounding plain, of a type that appears by the thousand across that same transition zone. There is a pleasing symmetry to the fact that the same Viking dataset also produced a crater in the southern hemisphere, Gall crater, which looks unmistakably like a smiling face. Nobody argued that one was built. The difference was never in the evidence. It was in what people wanted the evidence to be. Which brings us to why this entry opens the list rather than being left out of it. The face at Cydonia is the cleanest demonstration of the method every remaining entry depends on. The claim was specific. It made a prediction that better images would show more structure, not less. Better instruments were pointed at it 3 separate times across 30 years, and the prediction failed. That is not a disappointment. That is the process doing exactly what it is supposed to do, in public, slowly, with the data released each time. Hold on to one detail from that, because it comes back at the very end of this list. What settled the face on Mars was not an argument. Nobody talked anyone out of it. What settled it was a better camera. The one thing that does remain open here has nothing to do with Mars. It is the question of why human perception is so willing to find a face in low-contrast noise. The effect is called pareidolia, and it is not really a failure of reasoning, because reasoning arrives too late to be involved. The face detection system in the human visual cortex runs before conscious evaluation does, and it is tuned to accept false positives rather than risk missing a real face. In the environment that shaped it, Mistaking a rock for a person cost almost nothing. Mistaking a person for a rock could cost everything. So for 22 years, a great many people believed there was a monument on another planet. What changed their minds was not persuasion but resolution. And resolution, as we will see, is the one thing this entire list is short of. Better cameras settled that one over 22 years. The next entry took about a week. Number 19, The Doorway, in Mount Sharp. On the 7th of May, 2022, on mission day 3466, the Curiosity rover pointed its mast camera at a rock face on the lower slopes of Aeolis Mons. Aeolis Mons is the layered mound 5 kilometers tall that stands at the center of Gale Crater, and which the mission usually calls Mount Sharp. The rover has been climbing it, slowly, for more than a decade. The image that came back showed a doorway. That is not an exaggeration of what it looked like. In the frame, there is a rectangular opening set into a layered outcrop, with square corners, straight vertical sides, and a flat lintel across the top. It looks cut. It looks finished. It looks like the entrance to something. The image traveled further and faster than almost any other raw frame the mission has ever returned, and the correction came from the mission's own team within days. The correction was a number. The opening is roughly 30 centimeters tall and about 40 centimeters wide. It is not a doorway for anything larger than a cat. Set against a human hand, it would be about the span of 2 palms, and the outcrop it sits in is a low shelf a person could step over without slowing down. A word about the instrument, because it matters to how these images look. Curiosity's mast carries 2 cameras, one with a 34mm lens and one with a 100mm lens, mounted about 2 meters above the ground where a person's eyes would be. The doorway frame came from the longer of the 2, which compresses distance the way a telephoto lens does on Earth. A telephoto view flattens depth. It makes a shallow alcove look like a deep opening, and it removes most of the cues a wider lens would have given about how far away the rock was, and therefore how large it was. The image was not misleading on purpose. It was simply taken with the lens that removes the one piece of information a viewer most needed. Once the scale is known, the geology is straightforward. Sedimentary rock fractures along regular planes. Where 2 near-vertical joints intersect a horizontal bedding plane and the block between them falls out, the void left behind has square corners because the fractures themselves are planar. Geologists on Earth call these fracture-bounded alcoves, and they appear in sandstone outcrops on every continent. There is a version of this shape in almost every canyon in the American Southwest, and nobody has ever suggested those were built either. The interesting thing about that particular image is not the shape. It is that it belongs to a long and growing catalogue. Curiosity has been producing these for years. In 2015, it photographed a thin protrusion sticking out from a rock at an angle, casting a distinct shadow beneath it that looked exactly like a floating spoon. It is a ventifact, a rock sculpted by wind-driven sand, and it is thin because the softer material around it eroded away first. In 2014, it photographed something the internet immediately called a bone, which is a wind-carved fragment of the same kind. There has been a crab, a statue, a face in a cliff, and, in 2022, a formation about a centimeter across that looks remarkably like a flower. That one is genuinely lovely and entirely explicable. It is a diagenetic feature, formed when mineral-rich water moved through the rock and cemented material outward around a nucleus, and then the softer surrounding rock weathered away and left the harder shape standing. The scale of the place is worth holding in mind while these shapes accumulate. Gale crater is about 154 kilometres across, which is roughly the distance from London to Birmingham. Curiosity landed inside it on the 6th of August, 2012, and has driven more than 35 kilometres since, a little over 2 kilometres a year, which is about the pace of a slow walk spread across a decade. In that time, it has photographed hundreds of thousands of frames. Out of hundreds of thousands of images of broken rock, a handful will look like something. That is not a claim about Mars. It is a property of large numbers. Perseverance has added entries of its own, and one of them is worth dwelling on, because it inverts the whole exercise. In June 2022, Perseverance photographed what appeared to be a tangled bundle of string lying between two rocks in Jezero crater. It looked artificial, because it was. It is a fragment of Dacron netting, a material used in thermal blankets, shed by the rover's own descent stage during landing. That is not an isolated case. The landing scattered hardware across a wide area of Jezero, and the mission has since documented piece after piece of it: shreds of thermal blanket caught in rocks, fragments of netting, and the parachute and backshell lying intact on the surface, photographed both from orbit by the Mars Reconnaissance Orbiter and from the air by the Ingenuity helicopter in April 2022. Ingenuity flew over the debris field deliberately on its 26th flight to give engineers a look at how the hardware had performed. So there are confirmed artificial objects on Mars. There are more than a dozen of them scattered across Jezero crater alone, and rather more than that across Chryse Planitia, Utopia Planitia, Meridiani Planum, Gusev crater, and Elysium Planitia, where the earlier missions came down. Every one of them was made by us, and every one of them is exactly what an artificial object on Mars actually looks like when you find one: manufactured material, in an unnatural configuration, with no geological explanation available. That comparison is the useful part of this entry. The difference between a suggestive shape and a genuine artifact is not a matter of impression. It comes down to three things that can be measured. Scale, first, is the object sized for a purpose, or is it simply the size that geology makes things? Context, second, does it sit in a setting that would explain it, or does it interrupt one? And material, third, is it made of something the surrounding rock could produce? The doorway fails all three tests. It is the wrong size for a door. It sits in exactly the fracture pattern that produces such voids, and it is made of the same mudstone as the outcrop it is cut into. The netting passes all three, which is why nobody argued about that one. There is one more reason this entry sits at 19 rather than being left off the list. The speed of the correction is new. Curiosity's raw images are published automatically to a public website, usually within hours of reaching Earth, unprocessed and uncurated. That is why the anomaly cycle for this mission runs in days rather than the 22 years it took at Cydonia. The pictures arrive before anyone has had time to look at them properly, which means the public and the science team are looking at the same frames at roughly the same moment. That openness produces more claims, not fewer. It also settles them faster, which is a trade almost everyone involved considers worth making. Shapes are easy to argue about, because a shape is a matter of impression. The next entry is about something that can be measured, weighed, and compared against a monument that actually exists. Number 18. The pyramids that are not pyramids. About 20 kilometers from the Cydonia Mesa stands a five-sided hill. It was catalogued from the Viking frames in the late 1970s by two researchers whose initials it still carries, and it became known as the D and M pyramid. It has, in the low-resolution images, what appear to be five flat faces meeting at sharp edges, arranged with an apparent regularity that looked deliberate. A second group, and a more spectacular one, sits far away in Elysium Planitia. Mariner 9 photographed those in 1972, 4 steep-sided mounds standing on a plain, arranged in what looked like a grouping rather than a scatter. Photographs of them circulated for decades alongside the Cydonia images, usually with the same caption asking the same question. Mariner 9 deserves a moment of its own here, because it is the reason anyone had these pictures at all. It reached Mars in November 1971 and became the first spacecraft ever to orbit another planet. It also arrived in the middle of a planet-encircling dust storm, which meant that for weeks the surface below it was completely hidden and the mission had nothing to photograph but a featureless orange haze with 4 dark spots poking through the top of it. Those 4 spots turned out to be the summits of the Tharsis volcanoes and Olympus Mons, standing above the weather. When the dust finally settled, the spacecraft went on to map about 85% of the planet and return over 7,000 images and effectively every large-scale feature argued about since, including these mounds, comes from that single mapping campaign. The Elysium mounds were measured early, and the measurement ended the argument quickly, though the images kept circulating long after. The largest of them is roughly 3 kilometers wide at the base and about 1 kilometer tall. That number is worth sitting with because it is the whole entry. The Great Pyramid of Giza is about 230 meters along each side and about 146 meters tall. It is, by a wide margin, the largest structure any human civilization built by hand, and it took something like 20 years and a workforce in the tens of thousands. The largest Elysium mound is about 13 times taller than that, and around 13 times wider at the base. Volume scales with the cube of length, so the mound contains something on the order of 2,000 times the material. These are not pyramid-sized objects. They are mountain-sized objects that happen to have facets. And the reason mountains on Mars have facets is well understood, and it is one of the more genuinely interesting things about the planet. The dominant erosional agent on Mars is wind-carrying sand. There is no rain to speak of, no rivers running today, and no ice sheets grinding across the surface at these latitudes. What there is atmosphere in motion, and sand grains moving with it. Martian air is thin, about 0.6% of Earth's surface pressure, which is roughly the pressure you would find 30 kilometers above sea level here. Wind in air that thin carries very little momentum. A gale on Mars would barely stir a flag. But it has had 3 billion years. Sand carried by wind does most of its cutting close to the ground, in the lowest meter or two, because that is where the grains travel. It undercuts the base of a landform, the top collapses, and the process repeats. Where the wind blows predominantly from 1 or 2 directions, which it does over long periods, across much of Mars, the result is not a rounded hill. It is a landform with flat plains meeting at edges, aligned with the wind. The shape has a name. It is called a yardang, and Mars has the largest yardang fields anywhere in the solar system. Some of them run for tens of kilometers in parallel ridges, so regular that when radar analysts first mapped certain regions, they had to rule out an instrument artifact before accepting that the ground itself was that orderly. The Cydonia 5-sided hill was imaged at high resolution in the same 2001 campaign that settled the face, at about 1.5 meters per pixel. What it resolves into is an eroded massif with a slumped southern flank. Its apparent fifth face is a product of where the Viking-era shadow happened to fall, and the sharp edges soften considerably once the surface is properly lit. The 2001 imaging campaign was designed with the shadow problem in mind. Cydonia was photographed at several different sun angles rather than one, precisely so that nobody could argue afterwards that a single unlucky lighting geometry had flattened something real. A feature defined by shadow changes shape as the sun moves. A feature defined by rock does not. The mesa and the mound both changed. Mars Express stereo imagery in 2006 then produced an elevation model of the whole Cydonia group, and the model shows what a flat photograph never could. The mounds have internal layering. They have debris aprons at their bases, fans of material shed downslope over time. Those are the signatures of erosional remnants, of what is left after the surrounding ground goes away, and they are not what a built structure looks like in cross-section. It is also worth saying that Earth produces this shape without assistance. There are natural faceted pyramids in the Tibesti Massif of the Central Sahara, carved out of sandstone by wind in exactly the same way, and there are others in the deserts of Central Asia. None of them has ever been mistaken for architecture, mostly because people have walked up to them and put a hand on the rock. The difference between those hills and the Martian ones is not their shape. It is the distance. For scale on what Martian geology is capable of building without help, consider that the same planet contains Olympus Mons, a volcano about 22 kilometers tall with a footprint roughly the size of France, and Valles Marineris, a canyon system over 4,000 kilometers long and up to 7 kilometers deep. Against those, a 1-kilometer faceted mound is an unremarkable feature. There is one thing here that genuinely does not resolve, and it is a question about method rather than about Mars. There is no agreed statistical threshold at which a natural landform's regularity becomes evidence of design. On Earth, this is not a problem, because the question is settled by excavation. You dig. If it is a structure, there are courses of stone, worked surfaces, tool marks, cavities, and material brought from elsewhere. If it is a hill, there is bedrock. The question is closed in an afternoon with a trench. On Mars, nobody has excavated anything. Not once, not anywhere, not to any depth that would matter. That is not a rhetorical flourish, and it is not a complaint about secrecy. It is a literal description of the situation, and it becomes the subject of the final entry on this list. Every argument about whether a Martian landform is natural has been settled, where it has been settled at all, by pointing a better camera at its outside. The same wind that carved those facets has been at work on the entire surface of Mars for 3 billion years. It rounds, it strips, it buries, and it does not stop. That has a consequence which sits quietly underneath everything still to come on this list. Whatever has ever stood on the surface of Mars is, by now, either eroded away or buried under the material the erosion produced. Number 17. The Blueberries of Meridiani Planum. On the 25th of January 2004, a spacecraft wrapped in airbags bounced across the plains of Meridiani Planum, rolled to a stop, and came to rest inside a shallow depression about 22 meters across. Nobody had aimed for it. The landing ellipse was tens of kilometers long, and where inside it the lander finished was a matter of wind, bounce, and luck. It finished inside a small crater, later named Eagle, facing an exposed wall of bedrock about 12 meters away. That accident of trajectory has never been repeated. Every other landing on Mars has put a rover down on a plain, with the interesting rock somewhere over the horizon and weeks of driving in between. Opportunity opened its eyes already looking at an outcrop. Within days, the panoramic camera returned images of that outcrop, and the rock was studded with small grey spheres. They were embedded in the stone, weathering out of it as the surface eroded and collecting in loose drifts on the crater floor below. There were thousands of them in a single frame. The science team, looking at a pale rock full of small, dark, round things, called them blueberries, and the name stuck permanently. They are between 1 and about 6 millimeters across. They are almost perfectly spherical, and they are made largely of hematite, an iron oxide. That identification came quickly, from 2 instruments working together. The miniature thermal emission spectrometer read the mineralogy at a distance, and the Mossbauer spectrometer, an instrument built specifically to identify iron-bearing minerals by their nuclear response to gamma rays, was placed directly against the rock by the rover's arm. Within the first weeks of a mission designed to last 3 months, the composition was confirmed. Here is why that mattered enough to justify the landing site. Meridiani had been chosen for a reason, and the reason was hematite. Years earlier, the thermal emission spectrometer aboard Mars Global Surveyor had mapped the mineralogy of the whole planet from orbit and found a broad deposit of coarse-grained hematite at Meridiani, one of only a handful of such deposits anywhere. On Earth, that particular form of hematite is associated with water. So a rover was sent to a place selected on the strength of a color signature, read from 300 kilometers up, and the rock it landed in front of turned out to be full of the mineral the orbiter had detected, in the form of small spheres nobody had predicted. On Earth, hematite spheres of that size, distributed evenly through porous sediment, form in one dominant way. Iron-rich groundwater moves slowly through the rock. Where conditions change, a shift in chemistry, a change in acidity, the presence of a nucleus to build on, the iron comes out of solution and begins to precipitate, growing outward in all directions equally, which is what produces a sphere. Geologists call the result a concretion. They are common in the Navajo sandstone of southern Utah, where they weather out of the rock and litter the ground, and where locals have long called them Moqui marbles. The Utah concretions match the Martian ones so closely in size, shape, and distribution that they became the primary terrestrial comparison within weeks. There is a small detail about that instrument which says something about how these missions are built. The Mossbauer spectrometer worked by using a radioactive source, cobalt-57, to produce the gamma rays it needed. Cobalt-57 has a half-life of about 270 days. So the instrument's sensitivity decayed continuously from the moment it left Earth, and by the later years of the mission, a measurement that had once taken hours took days. The rover outlived its own instrument's ability to work quickly, and the team simply left it pressed against the rock for longer. The crucial detail is how the spheres sit in the rock. They are distributed evenly through it, at all levels, cutting across the layering rather than lying along it. If they had been grains washed in and deposited, they would be sorted into layers by size and weight, the way sand and gravel always are. They are not. They formed in place after the rock was already rock, which means water moved through that rock after it was buried. The blueberries were not the only evidence in that first outcrop, and they were not even the strongest. The same rock face showed cross-bedding, the diagonal internal layering that forms when sediment is carried by moving water and piles up on the downstream side of a ripple. Look at the bed of any shallow stream, and the same structure is forming there now. And the rock contained a mineral called jarosite, a hydrated iron sulfate that on Earth forms only in acidic water. Jarosite does not form dry. Its presence is a direct chemical statement that liquid water stood there. Then, 7 years later, came the clearest single piece of evidence the mission ever produced. In November 2011, having driven more than 20 kilometers from Eagle Crater to the rim of Endeavour Crater, a hole about 22 kilometers across, 1,000 times the diameter of the little crater where it had started, Opportunity photographed a bright white vein running through the rock. It was about 1 centimeter or 2 wide and perhaps half a meter long. The vein was nicknamed homestake, and analysis showed it to be calcium sulfate, gypsum. Gypsum in a crack does not form by any process other than water. Mineral-bearing water flows through a fracture, the water leaves, and what was dissolved in it stays behind, filling the crack from the walls inward. The mission's principal investigator described it publicly as the single clearest piece of evidence for water that the rover had found in 8 years of driving. Not the most complicated, the clearest. The strangest verified detail about all of this is not geological. It is about the machine. Opportunity was designed to operate for 90 Martian days. That was the mission. 90 days of driving, a kilometre of range if things went well, and then the dust would settle on the solar panels and the power would fall away and it would stop. It operated for 5,111 Martian days. It drove more than 45 kilometres, further than any vehicle has travelled on any world other than this one, and further than a marathon. Its power kept recovering because Martian dust devils passing over the rover repeatedly cleaned the panels, an effect nobody had designed for and nobody had counted on. Its twin, Spirit, which had landed 3 weeks earlier on the far side of the planet in Gusev crater, found silica deposits of the kind that on Earth form around hot springs, became stuck in soft soil in 2009, and carried on transmitting as a stationary science station for another year. Opportunity's final transmission came on the 10th of June 2018 as a planet-encircling dust storm closed over Meridiani and blocked the sunlight. It was a routine telemetry packet. The widely repeated line about a low battery and the dark coming was written afterwards by a journalist, and it is a good line, but it is not a message from Mars. What remains open here is narrower than it first appears, and it is important. The water at Meridiani is confirmed beyond argument. Whether it was ever hospitable is not. Jarosite requires acidity in a range that on Earth is tolerated by a small number of specialized organisms and is lethal to almost everything else. The water was there. Whether it was drinkable, in any biological sense, remains unresolved. Those spheres grew in groundwater, moving through buried rock. The next entry is about where all that water was coming from and where it was going. Number 16, the rivers that ran for 1 billion years. For most of the 20th century, the scientific verdict on Mars swung twice, and both swings came from a spacecraft. The first came on the 15th of July 1965, when Mariner 4 flew past Mars and returned 21 photographs. They were coarse, they covered less than 1% of the surface, and they showed craters. A dry, cratered, moon-like world with no sign of water and no sign of anything else. Those 21 frames effectively ended a century of speculation about canals and civilizations, and they did it in an afternoon. The second swing came 6 years later. Mariner 9 arrived in November 1971, entered orbit, and found the planet buried under a global dust storm. It waited. When the dust settled over the following weeks, the images that came back showed something nobody had prepared for. They showed valleys. Branching, tributary-fed valleys, hundreds of kilometers long, joining trunk channels at acute angles, the angles that only flowing liquid produces, because water joining water always meets it pointing downstream. Mariner 4 had photographed the wrong 1%. That same mission also found the canyon. Valles Marineris runs for over 4,000 kilometers along the Martian equator, reaches 7 kilometers deep in places, and is named after the spacecraft that discovered it. Laid over the United States, it would stretch from coast to coast, and its deepest point is 4 times the depth of the Grand Canyon. Mariner 9 went from photographing an orange blank to redrawing the map of an entire planet in the space of a few months. Those valley networks are concentrated in the ancient southern highlands, and their age can be estimated by counting the craters superimposed on them. The answer puts them in a period called the Noachian, roughly 4.1 to 3.7 billion years ago. Their drainage density, the total length of channel per unit area, is lower than that of terrestrial river systems, but it is consistent with sustained runoff fed from above rather than a single catastrophic release. Some of them carry a detail that is difficult to explain any other way. Nanedi Vallis in Xanthi Terra has an inner channel meandering along the floor of the larger valley. That is what a river does when it runs long enough to cut a bed inside its own valley and then continues running inside that bed. It is not what a flood does. A flood scours and leaves. Not every Martian valley was cut by rain, and the distinction is visible in their shapes. A network fed by precipitation has fine tributaries reaching up into the high ground, branching and branching again, like the veins of a leaf. A number of Martian valleys do not do this. They begin abruptly at a steep headwall, with no tributaries above them at all, and simply run downhill from there. That is the signature of groundwater sapping, water emerging under pressure from a subsurface aquifer, undermining the ground above it and causing the head of the valley to collapse and retreat. Both kinds are present on Mars, sometimes side by side, which means the planet had both rainfall and a working groundwater system. The strongest single piece of evidence sits at Jezero crater, where Perseverance landed on the 18th of February, 2021. Jezero has an inlet channel on its western rim, an outlet channel on its eastern rim, and at the mouth of the inlet, a fan-shaped deposit spread out across the crater floor. Seen from orbit, that fan has layered beds that slope gently outward and downward, foreset beds, the internal structure of a delta building out into standing water. Deltas require two things simultaneously: a river carrying sediment and a body of water still enough for the sediment to settle out. They are among the most unambiguous landforms in geology. The fan also carries boulders. Some are a meter across, and they were carried in from upstream and dumped where the current slowed. Moving a boulder that size requires flow with real energy behind it, which means the river was not a trickle and was not brief. Working from the elevation of the outlet breach, the crater held a lake roughly 45 kilometers across and, at its fullest, tens of meters deep. The outlet matters as much as the delta does. The crater filled until it overflowed and cut its way out the other side. A basin that fills to overflowing is a basin receiving more water than it loses, sustained, for a long time. Jezero is not unique, only well chosen. Eberswalder crater, further south, contains a delta so textbook in its form that it was a finalist landing site for Curiosity, with meander scars preserved in the sediment where the river channel swung back and forth across its own floodplain. Those meanders are a strong constraint. A channel only meanders if it flows steadily on a shallow gradient over a long period, which is not something a flood does on its way past. Gale crater tells the same story from the inside. Curiosity has spent more than a decade climbing through hundreds of meters of mudstone at the base of Mount Sharp, and the rock is finely laminated, layers a millimeter or less thick, stacked in their hundreds. That structure forms in one setting, still water, where fine particles settle slowly out of suspension and nothing disturbs them afterward. It is a lake bed, red in cross-section, and the rover has driven up through it layer by layer. The mission's estimate is that Gale held lakes, drying and refilling, over something between 100,000 and 10 million years, and the broader stratigraphy of the mound records a transition from wet conditions at the bottom to dry, sulfate-rich conditions higher up, spanning far longer. Curiosity is driving up through the record of a climate changing. The chemistry of the lowest layers is worth stating precisely, because it is easy to hear as a generality, and it is not one. The Yellowknife Bay mudstone, drilled in 2013, showed neutral acidity, low salinity, and a range of chemical elements in oxidation states that could supply energy to a microorganism. The mission described that environment publicly as habitable. That word has a technical meaning. It does not mean inhabited, and it does not mean likely. It means an environment in which a terrestrial microorganism could have made a living. And then there is the problem, which has not been solved. The sun 4 billion years ago was about 70% as bright as it is today. Stars brighten slowly as they age, and the young sun delivered substantially less heat to Mars than it does now. Mars, being further out, receives less than half the sunlight Earth does even at present. Run the numbers on early Mars with a plausible atmosphere, and the surface should have been frozen solid. No climate model has yet produced a Mars warm enough, for long enough, to run these rivers continuously. Carbon dioxide alone will not do it. Beyond a certain thickness, the gas condenses out into clouds and reflects sunlight back to space, which cools the planet rather than warming it. Adding hydrogen helps, adding methane helps, adding a haze layer helps, and none of the combinations proposed so far comfortably closes the gap for the required duration. The leading resolution is that the rivers did not run continuously. They ran in episodes. Large impacts inject enormous quantities of heat and vapor into an atmosphere and can produce warm, wet conditions lasting centuries to millennia. Major volcanic eruptions do something similar with sulfur and carbon dioxide. And Mars's axial tilt is not stable the way Earth's is. Earth's is held steady by the Moon, while Mars's wanders chaotically between roughly 0 and 60 degrees over millions of years, redistributing polar ice toward the equator and back. On that reading, the valley networks were carved over 1 billion years by a planet that thawed repeatedly and briefly and froze in between. The valleys exist. They were cut by water. The mechanism that supplied the warmth does not yet add up, and that gap is one of the more honest, open problems in planetary science. The number worth carrying forward is the duration. Whether the water ran continuously or in bursts, the wet period on Mars spans something on the order of 1 billion years. For comparison, complex animal life has existed on Earth for a little over half that. Mars was a world with rivers for longer than this planet has had anything more complicated than a worm. All those rivers were running downhill toward the same third of the planet. The next entry is about what may have been waiting for them there. Number 15. The shoreline of a vanished ocean. Roughly a third of Mars is missing. That is not a figure of speech. The northern third of the planet sits between 1 and 3 kilometers lower than the southern 2/3, and the boundary between them runs most of the way around the globe. It is called the crustal dichotomy, and it is the single largest topographic feature on any rocky world in the solar system. Nothing on Earth, Venus, or Mercury approaches it. The two halves are different in more than height. The southern highlands are heavily cratered, which means they are old. Craters accumulate over time, so a surface covered in them has been sitting undisturbed for billions of years. The northern lowlands are comparatively smooth and comparatively young in crater count. Something resurfaced them. The crust beneath them is also measurably thinner, which some models attribute to a single enormous impact very early in Martian history, one large enough to have removed a substantial fraction of the northern crust in a few hours. Whatever made the basin is there. It is the lowest ground on the planet. It covers around a third of the surface, and for 1 billion years, every river on Mars was running toward it. In 1989, working from Viking imagery, geologists traced what appeared to be 2 contact lines running for thousands of kilometers around the margin of that lowland. They looked like shorelines, the boundary where a standing body of water had met the land, marked by a change in texture, a terrace, a break in slope. The proposed ocean was given a name, Oceanus Borealis. There are 2 of them, and they are not the same age. The higher and older is called the Arabia contact, which, if real, would mark a very large early ocean. The lower and younger is called Deuteronilus, and it is by far the better preserved of the 2, a more continuous line with clearer terracing enclosing a smaller sea. That pairing has its own implication. 2 shorelines at 2 elevations describe a body of water that stood high once, fell, and stood again at a lower level, which is the profile of an ocean drying out in stages rather than vanishing in one event. The proposal was strong on shape and weak on physics, and the weakness was fatal in its original form. A shoreline must be level. Water finds a single surface, and that surface follows gravity. On any planet with a settled shape, a shoreline traced around a basin should return to the same elevation it started at. These did not. The proposed contacts varied by several kilometers along their length, which for a shoreline is not a small discrepancy. It is a disqualification. The rescue came from an unexpected direction, and it is one of the more satisfying pieces of reasoning in Martian geology. Mars is dominated by Tharsis, a volcanic province about the size of North America that rises up to 7 kilometers above the surrounding datum and carries the largest volcanoes in the solar system on its back. Tharsis is so massive that it did not simply sit on the crust, it deformed the entire planet as it grew, flexing the lithosphere and altering the shape of the gravitational surface across the whole globe. Anything that was level before Tharsis finished growing is not level now. It is worth pausing on how strange that bulge is as an object. Tharsis carries Olympus Mons, Ascraeus Mons, Pavonis Mons and Arsia Mons, 4 of the largest volcanoes in the solar system, and it represents an accumulation of erupted rock so large that it shifted the planet's rotational balance. Mars physically reoriented itself around the new mass distribution, tipping the whole crust relative to the spin axis. When a feature is large enough to move the poles of the planet it sits on, warping a shoreline by a few kilometers is a modest side effect. So the calculation was run backwards. Take the present topography, model the deformation Tharsis imposed, and remove it. When that correction is applied, the proposed shorelines flatten out to near constant elevation, which is precisely what would happen if they had been level when they formed and had been warped afterwards by the growing bulge. That calculation was only possible because of an instrument that spent 2 years doing something unglamorous. The Mars Orbiter Laser Altimeter aboard Mars Global Surveyor fired a laser pulse at the surface 10 times a second and timed the return. Between 1999 and 2001, it measured the elevation of Mars more than 600 million times to a vertical precision of about 30 centimeters. That dataset remains the topographic foundation for essentially every Mars mission flown since, and it is the reason anyone could test the shoreline claim at all. The implied volume is substantial. Estimates for the larger of the 2 proposed contacts correspond to a body of water containing something on the order of 20 million cubic kilometers. The Arctic Ocean holds about 18 million. So this is an ocean in the ordinary sense of the word, covering roughly a third of the planet, with a maximum depth in the deepest part of the basin measured in kilometers. There is also evidence from the ground, which is rarer and therefore worth more. The Zhurong rover landed in Utopia Planitia on the 15th of May, 2021, well inside the proposed ocean basin. It carried ground-penetrating radar, and it drove across the terrain returning subsurface profiles as it went. Those profiles show layered structures reaching down tens of meters, interpreted by the mission team as sequences of sediment laid down in episodes. At the surface, the rover imaged features the team described as consistent with a coastal setting: troughs, pitted cones, and material that appeared to have been sorted by water rather than by wind. One result from that rover cuts against the more optimistic readings, and it deserves to be stated alongside the rest. Zhurong's radar reached about 80 meters below the surface along its traverse, and it found no liquid water at any depth it could see. Layered sediment, yes. Buried structure, yes. Standing or saturated water in the upper 80 meters of the old sea floor, no. Whatever became of the ocean, it did not simply sink into the ground and stay there within reach. Utopia Planitia is itself an enormous feature, the largest recognized impact basin on Mars, about 3,000 kilometers across, and the place where Viking 2 set down on the 3rd of September, 1976. Two spacecraft, 45 years apart, landed inside what may have been the floor of a sea. What remains open is duration, and this is where the entry becomes genuinely uncertain. Mars has outflow channels, and they are on a scale that has no terrestrial equivalent. Cassae Valles and Ares Valles are over 100 kilometers wide in places, with streamlined islands standing in the middle of them where the current parted around high ground. The discharges required to cut them are estimated at something like 10,000 times the flow of the Mississippi, released catastrophically, probably when pressurized groundwater broke through a confining layer. A flood on that scale could fill the northern basin in weeks. And an ocean produced that way, on a cold planet with a thin atmosphere, would freeze over within centuries and then sublimate away, leaving shorelines behind it and never once having been a stable sea. A long-lived ocean is a different proposition entirely. It requires a thick, warm atmosphere sustained for a very long time, and that runs directly into the climate problem from the previous entry, the one nobody has solved. The shorelines cannot distinguish between these two histories. They record that water stood at that level. They say nothing about how long it waited there. The difference matters more than almost anything else on this list. A brief, frozen, catastrophic ocean is a geological event. A stable sea lasting hundreds of millions of years is an environment, and environments are where things happen. An ocean that size does not simply evaporate quietly. The next entry is the receipt. Number 14, the water Mars lost. There is a way to weigh an ocean that no longer exists. It is one of the more elegant measurements in planetary science, and it depends on the fact that not all hydrogen is the same. Ordinary hydrogen has a single proton in its nucleus and nothing else. Deuterium has a proton and a neutron, which makes it twice as heavy. Both behave identically in chemistry. Both form water. A molecule of water built with a deuterium atom instead of an ordinary one is called heavy water, and it is chemically indistinguishable from the ordinary kind in almost every way that matters. Almost every way. There is one difference, and it is decisive. When a planet's atmosphere leaks into space, the escape process is mass selective. Lighter particles reach escape velocity more easily than heavier ones, so ordinary hydrogen escapes preferentially and deuterium is left behind. Over time, the water that remains becomes progressively enriched in the heavy isotope. The ratio between the two is therefore a receipt. It records how much water a planet has lost, because the enrichment depends on how much of the light isotope has been carried away. Mars's atmosphere is enriched in deuterium relative to Earth's oceans by a factor of roughly 5 to 6. That is not a subtle result, and it is not an ambiguous one. Earth's seawater contains about 156 deuterium atoms for every million hydrogen atoms, and that value is used as the reference standard for the entire field. Mars sits several times higher. The only way to reach that value is to have started with something close to the terrestrial ratio and then lost the overwhelming majority of the light hydrogen, which means losing the overwhelming majority of the water. In 2015, astronomers used the Keck Observatory in Hawaii and the Very Large Telescope in Chile to map that ratio across the disk of Mars, distinguishing ordinary water vapor from heavy water vapor by their infrared signatures. The measurement was done from Earth at a distance of tens of millions of kilometers, and it produced a map of the enrichment varying by latitude and by season. The seasonal variation in that map was itself informative. The enrichment is not uniform across the planet. It changes with latitude and with the Martian year, which means water is still cycling between the polar caps, the atmosphere and the ground today, on an annual rhythm, in quantities small enough to be invisible and large enough to measure from another planet. Converted into a volume, the result is this. The water Mars has lost corresponds to a layer at least 137 meters deep, spread evenly over the entire planet. Water does not spread evenly, though. It pools in the low ground. Concentrated into the northern basin, the same volume becomes an ocean covering close to a fifth of the planet's surface, more than a kilometer deep at its deepest point. That is an independent measurement, arrived at by an entirely different method, and it lands in the same range as the shorelines from the previous entry. Two lines of evidence, one geological and one isotopic, converging on a Mars that had an ocean. The mechanism was then watched directly. Methane entered orbit around Mars on the 21st of September, 2014, with a single job, to observe the atmosphere leaving. Its instruments measure the composition of the upper atmosphere and the ions streaming away from it, and it flies through the region where the loss happens. What it found is that the solar wind, the continuous flow of charged particles from the Sun, reaches the Martian upper atmosphere directly and strips ions from it, carrying them away. The present-day rate is not large. It runs at something on the order of 100 grams per second, which is roughly a bucket of water an hour, and by itself, that is not enough to matter over any timescale a person would care about. But the rate is not constant, and it was not always this low. In March 2015, Methane observed a solar storm arrive at Mars, and during that event, the escape rate rose by a factor of more than 10. Storms of that kind were far more frequent when the Sun was young. Young stars rotate faster, have stronger magnetic activity, and emit far more ultraviolet radiation and far more energetic particles. 4 billion years ago, the Martian upper atmosphere was being scoured at rates that dwarf anything Methane has recorded. 100 grams a second is negligible. 100 grams a second, multiplied across 4 billion years and multiplied again by the far higher rates of the early solar system, is an atmosphere. Methane, incidentally, has now been doing this for more than a decade, well past its planned mission, and its measurements have become the baseline record of how a planet loses an atmosphere. It also serves as a communications relay for the rovers on the surface, which means the spacecraft watching Mars lose its air is the same one carrying the drill results home. The escape also leaves other fingerprints, and they all point the same way. Argon on Mars is fractionated. The lighter isotope, argon-36, is depleted relative to the heavier argon-38, exactly as escape would predict. Carbon and nitrogen show the same pattern, This becomes important several entries from now, because it means the isotopic oddities of the Martian atmosphere are not a collection of separate puzzles. They are one process, leaving the same signature across the periodic table. There is one part of this that complicates the picture, and it improves the situation rather than worsening it. Not all of the missing water went to space. A substantial fraction never left at all. When water reacts with rock, when basalt weathers, when clays form, the water is not simply sitting in pores. It is incorporated into the crystal structure of the minerals themselves, chemically bound, part of the rock. Analysis of Martian crustal chemistry suggests that the quantity locked away this way may be comparable to the quantity that escaped. That water is still on Mars. It is in the rock, it does not participate in the atmosphere, and it therefore does not register in the isotopic budget at all. Getting it out requires heating the rock to several hundred degrees, which is a real prospect for a future crew, and no prospect at all for anything that lived there. Then there is the ice, which is confirmed and visible. On the 20th of June, 2008, the Phoenix lander scraped a shallow trench near the Martian North Pole and exposed bright white material a few centimeters below the surface. Over the following days, the camera watched several small chunks of it disappear. Rock does not disappear. Salt does not disappear. Water ice, at Martian pressure, sublimates directly into vapor, and that is what the images recorded, frame by frame, over 4 days. So the missing water had 3 possible fates, and all 3 are real. Some escaped to space. Some froze into the ground and the polar caps. Some was chemically bound into the crust. The proportions are genuinely disputed, and current estimates differ by factors of several, which is a polite way of saying nobody knows the split. The context number for present-day Mars puts the loss in perspective. Surface atmospheric pressure there is about 610 pascals, roughly 0.6% of Earth's. That value sits very close to the triple point of water, the pressure below which liquid water cannot exist at all, and ice passes straight to vapor. Across most of the planet, on most days, water simply cannot be liquid. It has no stable state between ice and gas. The thing to hold on to is the pace. None of this happened quickly. There was no moment when the ocean drained. The atmosphere thinned across hundreds of millions of years. The pressure fell below the threshold gradually. The shoreline retreated slowly enough that no single generation of anything would have noticed it moving. Almost all of it went. The next 3 entries are about the fraction that may not have. Number 13. The streaks that come back every summer. On steep slopes across the equatorial and mid-latitude regions of Mars, something appears every summer. Dark, narrow lines emerge on the warmest faces of crater walls and canyon flanks. They extend downhill over a period of weeks, growing longer as the season progresses. They are typically between 0.5 meter and 5 meters wide, and the longest run for several hundred meters. Then, as the cold returns, they fade. The following year, in the same places, on the same slopes, they come back. They are called recurring slope lineae, and their discovery is a small story about looking properly. In 2010, an undergraduate at the University of Arizona named Lujendra Ojha was working through images from HiRISE, the high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter, a camera that resolves objects about 30 centimeters across from an altitude of roughly 300 kilometers. He was comparing images of the same terrain taken at different times, and he noticed features that were present in one and absent in another. Repeated comparisons showed the pattern: appear, extend, fade, return. Thousands of candidate sites have since been catalogued, concentrated in Valles Marineris and in craters of the southern mid-latitudes. The temperature correlation was the part that made everyone sit up. The lineae appear where and when surface temperatures rise above roughly 250 Kelvin, which is about minus 23 degrees Celsius. That is far too cold for pure water. It is not too cold for brine. The Phoenix lander had confirmed in 2008 that Martian soil contains perchlorate salts at around 0.5% by weight. Perchlorates are extraordinary at depressing the freezing point of water. A saturated calcium perchlorate brine stays liquid down to around minus 70 Celsius. So the chemistry needed to make liquid water at minus 23 degrees is not exotic on Mars. It is already in the dirt. Perchlorates are worth a short detour, because they turn up repeatedly on this list, and they are not a minor detail of Martian soil chemistry. They are chlorine compounds, they are strongly oxidizing, and they are present essentially everywhere anything has landed. For a future crew, they are a direct problem. Perchlorate interferes with the human thyroid's uptake of iodine, and at the concentrations measured in Martian dust, it would need to be removed from any soil used for growing food and washed off anything brought inside. For the chemistry of Mars, they are a complication of a different kind, and one that returns in a much more consequential form a few entries from now. In September 2015, NASA held a press conference. Spectral observations from the orbiter's imaging spectrometer had detected hydrated salts in the lineae, and, crucially, only when the lineae were present. When the streaks faded, so did the signature. The announcement was framed as evidence of flowing liquid water on present-day Mars, and for about 2 years, it was the most widely reported Mars result of the decade. It reached front pages. It changed how the planet was discussed. Then it was substantially undone, and almost nobody heard about that part. The first problem was topographic. In 2017, an analysis of the terrain profiles beneath hundreds of lineae found that the streaks consistently terminate at slopes near the angle of repose for loose granular material, around 30 degrees. That number is the maximum angle at which dry sand will sit before it slides. Below it, sand stops moving. Water does not behave that way. Water flowing downhill continues onto gentler ground, spreads, ponds, or soaks in. Something that stops precisely where dry sand stops is behaving like dry sand. The second problem was spectral. Later work showed that the hydrated salt signal could arise from the way the instrument averages light across a single pixel. The spectrometer's pixels are much larger than the streaks themselves, so each measurement mixes the streak with the surrounding ground. Under certain conditions, that mixing can produce an apparent hydration signature without there being additional hydrated material in the streak at all. The third line of evidence pointed elsewhere entirely. Studies linked the flows to dust activity and to gas-triggered granular movement, the idea that seasonal sublimation of small quantities of frost, or the release of trapped gas as the ground warms, can destabilize a slope enough to start a dry avalanche of fine material. That would explain the seasonality, the temperature threshold, and the repetition without any liquid water at all. There is a further difficulty underneath all of this, which applies to any wet interpretation. At Martian surface pressure, around 610 pascals, close to the triple point of water, liquid water is barely stable at all. Pure water exposed at the surface tends to boil and freeze almost at the same time, losing mass to vapor while dropping in temperature. Brine helps because dissolved salt lowers both the freezing point and the vapor pressure, but even brine on a sunlit Martian slope is losing water to the atmosphere while it flows. Any liquid involved in these streaks is not a stream. At most, it is a damp film in the top few millimeters of the soil, moving grain by grain. The current position is genuinely unsettled, and it is worth stating exactly where it sits, rather than rounding it off in either direction. The consensus has moved substantially toward dry granular flows, possibly triggered or lubricated by very small amounts of atmospheric water or frost, enough to matter chemically, nowhere near enough to constitute a habitat. But the question has not closed. Work published as recently as 2025 has revived a limited water interpretation, arguing from the time series behavior of individual streaks that some of them are compatible with water reaching the surface from bedrock aquifers melting at depth. The scale of the seasonal growth is worth a number. At some sites, the lineae extend several hundred meters over the course of a single Martian summer, then fade entirely, then reappear the following year within a few meters of where they ran before. That repeatability is the strongest single argument that whatever produces them is tied to a fixed source in the slope rather than to loose material that happens to be sitting there. The features are real. They are seasonal. They repeat with a fidelity that rules out one-off landslides. Their cause is not settled, and the people arguing about it agree on the images and disagree on the physics. There is one practical consequence of all this that is easy to miss and rather large. When the 2015 result was announced, the recurring slope lineae sites were formally designated as regions requiring special planetary protection precautions. That designation is not symbolic. It restricts where spacecraft may be sent, because a spacecraft carrying terrestrial microorganisms into a place where liquid water might exist could contaminate the very environment a future mission would be sent to examine. Rovers have been kept away from these slopes. Landing sites have been evaluated against them. So a result that has been substantially walked back is still, in effect, shaping where hardware is allowed to go, which is the correct outcome given the uncertainty, and a good illustration of how these decisions are actually made. When the cost of being wrong is contaminating the only sample you will ever get, you stay back. The other thing worth carrying forward from this entry is the shape of the story itself, because it recurs on this list. A careful observation is made. A cautious interpretation is offered. The interpretation is reported without its caveats, becomes the headline version, and then quietly erodes over the following years while nobody is watching. The original observation, dark streaks that grow in summer and fade in winter, was true the whole time, and remains true, and is still not explained. Those streaks may well be dry. What sits under the southern ice cap is a considerably harder argument to dismiss. Number 12. The lakes beneath the southern ice. The Mars Express orbiter carries an instrument that nearly never worked at all. It is called MARSIS, the Mars Advanced Radar for Subsurface and Ionosphere Sounding, and it does something no camera can. It transmits low-frequency radio pulses downward, and those pulses pass through ice and dry rock rather than reflecting off them. Wherever the pulse crosses a boundary between materials with different electrical properties, part of it reflects and returns. By timing the returns and measuring their strength, the instrument builds a profile of what lies beneath the surface, down to kilometers of depth. To do that, it needs very long antennas, and MARSIS has 2 of them, each 20 meters long, made to be unfurled from a canister after arrival. When the time came, the engineers hesitated. Modeling suggested the booms might not deploy cleanly, that one could whip back and strike the spacecraft on release, ending the mission. So the antennas stayed in their canisters while the analysis was redone, and redone again. They were finally released in 2005, 18 months after Mars Express reached orbit. They deployed correctly. In July 2018, a team led by Roberto Orose reported what the instrument had found beneath the South Polar layered deposits in a region called Ultimi Scopuli at about 81 degrees south. There was a bright reflection at the base of the ice, roughly 1.5 kilometers down, extending across an area about 20 kilometers wide. It was unusually strong, brighter in fact than the reflection from the surface of Mars itself, which is an unusual thing for a buried boundary to be. On Earth, that specific radar signature has a specific meaning. It is the signature used to identify subglacial lakes beneath the Antarctic ice sheet, of which more than 400 are now known, including Lake Vostok, which sits under nearly 4 kilometers of ice and holds liquid water at around -3°C. Water reflects radio waves far more strongly than rock or ice does, because its electrical permittivity is so much higher. A basal reflection brighter than the surface is what water looks like from above. In 2020, with more observations, the team reported additional smaller bright patches surrounding the main one, suggesting not a single lake, but a system of separate bodies, the way subglacial water on Earth tends to be distributed. Follow one pulse down, and the strangeness of this measurement becomes clear. The spacecraft is 300 kilometers above the southern ice, moving at several kilometers a second, and it releases a pulse of radio energy downward. The pulse reaches the surface in about 1,000th of a second. Most of it bounces straight back, and that return is the surface echo, the bright line that marks where the ground is. But part of the pulse keeps going. It enters the ice and travels through it, slowing slightly, spreading, weakening. It passes through layer after layer of dust and frozen water, each boundary taking a little more of its energy and sending it back upward as a fainter and fainter signal. Down through several hundred meters, down through a kilometer. The returns coming back are now very small, and the instrument is stacking thousands of pulses together to pull them out of the noise. Then, at about 1.5 kilometers, something comes back strong. It arrives brighter than the surface return did, a boundary reflecting more energy than the top of the planet reflected. There is only one common substance that does that, and there is no camera anywhere that could photograph it, because it is buried under 1.5 kilometers of ice at 81 degrees south. The only way anyone will ever see it is like this, as a number in a stack of returns, from a pulse that went down and came back and took a fraction of a second to do it. The interpretation carries a demanding condition. At that depth, under that ice, the temperature is around -68°C. Nothing stays liquid at -68 unless it is extraordinarily salty. The requirement is a brine saturated with perchlorate salts, most plausibly calcium or magnesium perchlorate, which are the compounds that keep water liquid to the lowest temperatures anyone has measured. That is not water anything known on Earth would live in. It is far beyond the salt tolerance of even the most extreme terrestrial halophiles, and the cold compounds the problem. But it is liquid, it is water, and it would be the only standing liquid water on Mars. The challenge arrived from several directions at once, and it has not resolved. The first objection was thermal. Modeling the temperature structure of the South Polar Cap makes it difficult to get the base warm enough for liquid to persist, even allowing for brine. Closing that gap generally requires a local heat source, a magma body emplaced within the last few 100,000 years, sitting under that particular patch of the polar cap. That is possible. It is also unobserved, and invoking a conveniently placed subsurface magma chamber to rescue an interpretation is the kind of move that makes reviewers uncomfortable. The second objection was material. In 2022, an analysis argued that certain clay minerals, particularly smectites, can produce a bright basal reflection when frozen, with no liquid involved at all. Smectites are common on Mars and would plausibly accumulate at the base of a polar cap. Other work has argued the opposite, calculating that even water-rich clay at polar temperatures does not reach the permittivity the observation requires. A third line pointed at the ice itself, suggesting that layers of alternating composition could produce constructive interference, the returns from many closely spaced boundaries adding together to mimic a single strong reflection. And then a fourth line cut the other way. A topographic study examined the surface of the ice cap directly above the bright region and found the specific pattern of subtle depression and slope that liquid water beneath ice produces on Earth, where the ice floats slightly and its upper surface responds. That is independent evidence from a completely different measurement, and it supports the water reading. So the situation is this. The bright reflectors are real and reproducible. 4 separate explanations are live. The people involved agree on the data and disagree on the physics, in the open literature, and have done so for years. There is a further complication that keeps the argument from closing. NASA's SHARAD instrument aboard the Mars Reconnaissance Orbiter has also looked at this region, and it has repeatedly failed to detect the same feature. That sounds decisive until you look at the frequencies. SHARAD operates at higher frequencies than MARSIS, which gives it better vertical resolution and much worse penetration through the dusty ice above. A non-detection by an instrument that may not be able to see that deep is weak evidence, but it is not nothing, and it is regularly cited on both sides. The polar layered deposits themselves are worth a sentence, because they are one of the finest records in the solar system. They are a stack of alternating ice and dust, up to about 3.5 kilometers thick, laid down as Mars's axial tilt and orbital shape varied over millions of years and shifted where ice was stable. Read properly, they are a climate archive in the same way that Antarctic ice cores are, and nobody has ever read one, because reading one requires drilling into it. The strangest verified detail here is about time. This argument has now run longer than the mission that started it was originally designed to last. Mars Express entered orbit on the 25th of December, 2003, on a nominal mission of 1 Martian year. It has been operating for more than 2 decades and is the longest-serving European spacecraft at another planet. And the argument cannot be settled with anything currently at Mars. Confirming or excluding subglacial water requires either a radar operating at lower frequencies than MARSIS or a lander at the South Pole with a drill. Neither is scheduled. Neither is funded. The question will stay open not because it is unanswerable, but because nobody has sent the instrument that would answer it. If there is standing liquid water on Mars right now, it is a briny lake sitting under 1.5 kilometers of ice at 81 degrees south, in the dark, at -68 degrees, and it has been sitting there undisturbed for a very long time. Water is the setting for everything on this list. The next entry is the first thing on it that behaves as though something is being made. Number 11. The methane that comes and goes. Methane should not exist on Mars. That is the first thing to understand about this entry, and everything else follows from it. Methane is a simple molecule, 1 carbon atom and 4 hydrogens, and it is fragile in sunlight. Ultraviolet radiation breaks it apart. Calculate how long a methane molecule survives in the Martian atmosphere, and the answer comes out at roughly 300 years. On a planet 4.5 billion years old, 300 years is nothing at all. It is the last blink, which means that any methane detected in the Martian atmosphere today was put there recently. Not 4 billion years ago. Not in the wet period. Recently, on a human scale, by something that is still operating. The second thing to understand is where methane comes from on the only planet where we can check. On Earth, more than 90% of atmospheric methane is produced by living things, by microorganisms in wetlands and sediments and the digestive tracts of animals, and by the decay of organic material. Methane is not proof of life. But on Earth, methane is mostly life. So the detection of Martian methane was always going to be the most closely watched trace gas measurement in planetary science, and it has become the most contested. Curiosity carries an instrument called the Sample Analysis at Mars Laboratory, and it has been measuring the atmosphere inside Gale Crater since 2012. It works by drawing in Martian air and concentrating it, pulling the gas through a trap over many hours, which accumulates trace species until they are abundant enough to measure. That is why its readings are integrated over time, rather than instantaneous. What it found is a background level of about 0.4 of a part per billion by volume, varying with the Martian seasons, peaking in northern summer. A seasonal cycle implies a reservoir that responds to temperature, something being absorbed onto the surface when it is cold and released when it warms, which would be an ordinary physical process rather than an active source. Against that background, the instrument has recorded spikes. In late 2013 and early 2014, it measured a sustained elevation of around 7 parts per billion, more than 10 times the background, which persisted for roughly 2 months and then went away. In June 2019, it recorded about 21 parts per billion by volume, roughly 50 times the background and the largest reading the mission has produced. It is worth pausing on how small these quantities are, because the numbers are easy to hear as ordinary, and they are not. A part per billion is one molecule in 1,000 million. Earth's atmosphere carries methane at close to 2,000 parts per billion. The largest spike ever recorded on Mars, the one that made headlines, was 21 parts per billion, about 1% of the ordinary background concentration in the air in this room. These instruments are arguing about a gas present at 1/100th of the level that a person breathes without noticing, in an atmosphere that is itself less than 100th the density of ours. And here the record breaks in half. The ExoMars Trace Gas Orbiter arrived at Mars in 2016, carrying spectrometers built for precisely this measurement, and built to be roughly 1,000 times more sensitive than the rover's instrument. It scans the atmosphere at the limb, looking through a long path of air at sunrise and sunset, which is the most sensitive geometry available for detecting a trace gas. Its published upper limit for atmospheric methane is around 0.05 of a part per billion. That is below the level the rover reports as its ordinary background. The most sensitive instrument ever sent to look for methane at Mars has not detected any methane at all. During the June 2019 spike, the orbiter passed over the same region within days on either side and found nothing. Both instruments work. Both teams have examined their calibrations and stand by their data. And these are not two amateur measurements. They are the two most carefully built trace gas detectors ever flown to another planet, and they disagree about whether a gas is present. The leading reconciliation is atmospheric rather than instrumental, and it is ingenious. Mars has a strong daily cycle in its lower atmosphere. At night, the surface cools rapidly, and the air above it becomes stably stratified, cold, dense air sitting still near the ground with warmer air above it, and very little vertical mixing. A gas seeping out of the ground at night would pool in a thin layer near the surface, exactly where the rover's inlet sits, and could reach concentrations of a few parts per billion in that layer, while the atmosphere as a whole contained almost none. Then the sun rises, the surface heats, convection begins, and the boundary layer rises to several kilometers. The pooled gas is mixed upward into a volume perhaps 1,000 times larger, and its concentration falls below anything the orbiter can detect. That explanation accounts for a great deal. Curiosity measures mostly at night, because its instrument requires power that is easier to spare when other systems are idle. The orbiter measures at sunrise and sunset in the mixed atmosphere, looking through the whole column. But the reconciliation has a cost, and the cost is significant. For this to work, the methane must be destroyed far faster than ultraviolet photolysis destroys it. Otherwise, it would accumulate in the global atmosphere over years, and the orbiter would see it. That requires an unknown surface process removing methane quickly, possibly the abrasion of dust grains generating reactive chemistry at the surface, possibly reactions with the perchlorates and oxidants already known to be in the soil. There is a further wrinkle in the timing that emerged later, and that fits this picture. Analysis of the rover's measurements found not only a seasonal cycle, but a daily one. Methane higher at night, lower during the day, in the same location, on the same instrument. That is exactly what a near-surface layer being mixed away each morning would produce. And it is one of the stronger arguments that the reconciliation is on the right track. So resolving the contradiction requires introducing a destruction mechanism nobody has identified. The source is equally unresolved, and it is important to be careful here because this is the entry on the list where careful reasoning matters most. Non-biological production is entirely plausible and requires nothing exotic. Serpentinization, the reaction of water with olivine-rich rock, which is abundant on Mars, produces methane and hydrogen as byproducts, and is expected to be occurring in the Martian subsurface wherever water contacts the right minerals. Ancient methane trapped in clathrates, which are cages of water ice that hold gas molecules and release them when destabilized, is plausible. Methane generated long ago and slowly leaking through fractures is plausible. Biology is also, formally, plausible. Methane-producing microorganisms are among the oldest and simplest metabolisms on Earth. They require no sunlight, and they thrive in exactly the kind of warm, wet rock the previous entries have established Mars once had and may still have at depth. Nothing measured so far distinguishes between these possibilities. The measurement that would distinguish them exists, and it has not been made with the necessary precision. Biological processes prefer the lighter carbon isotope, carbon-12, over carbon-13. Methane produced by living things carries a measurably different isotopic ratio from methane produced by rock chemistry. That measurement requires precision beyond what any instrument on Mars can currently deliver, and it is a stated objective for samples returned to Earth. There is one more piece worth mentioning, because it makes the picture stranger rather than clearer. Mars Express also reported methane detections from orbit, including one in 2013 that appeared to coincide with a rover spike. The Trace Gas Orbiter, meanwhile, has searched for other biologically interesting gases, ethane, phosphine, and found none of those either. A gas that should not exist appears on Mars, disappears, and reappears, and the two best instruments ever sent to look at it cannot agree that it is there at all. Methane is a very small molecule. The next entry is about the largest ones anyone has ever found there. Number 10, the largest organic molecules on Mars. We are halfway down, so it is worth taking a moment to look back up the list at what has already changed. We began with a mesa that turned out to be a mesa, a doorway 30 centimeters tall, and a set of mountains mistaken for monuments. Then the list stopped resolving claims and started accumulating them. Spheres of hematite that grew in groundwater. Valleys cut by rivers that ran for something like 1 billion years. A basin covering 1/3 of the planet with 2 shorelines around its rim. Hydrogen isotopes that weigh the ocean that filled it. streaks that return every summer for reasons nobody agrees on, and a bright reflection under 1.5 kilometres of polar ice that 4 different explanations are still competing for. And a gas appearing in an atmosphere that should destroy it within 3 centuries. Nothing so far has been life. Everything so far has been the conditions for it, and the conditions have been getting harder to dismiss with every entry. Which brings us to the chemistry. In May 2013, on mission day 279, Curiosity drilled a mudstone target called Cumberland in a place called Yellowknife Bay near the base of Mount Sharp. Yellowknife Bay is an ancient lakebed. The rock is roughly 3.7 billion years old, laid down grain by grain in still water when Mars was young and wet. Yellowknife Bay had already produced the single most consequential sentence of the mission. When the first Cumberland and John Klein samples were analyzed in 2013, the chemistry came back showing neutral acidity, low salinity, and a set of elements present in more than one oxidation state, meaning there were chemical energy gradients available, the kind a microorganism could feed on. The mission stated publicly that this had been a habitable environment. That word is doing precise technical work and no more. It does not mean inhabited. It does not mean probable. It means that if a terrestrial microorganism had been placed in that lake 3.7 billion years ago, it could have made a living there. That was the first time anyone had been able to say that about a specific place on another planet. The powdered sample was delivered to the sample analysis at Mars Laboratory in the rover's body, analyzed and reported. And then portions of it were kept, sealed inside the rover, unused, sitting on Mars. They sat there for 12 years. In that time, the mission team learned a great deal about how their own instrument behaved. The laboratory works by heating a sample to release the gases trapped in it, and then separating and identifying those gases. The standard procedure heated the sample all the way to around 850 degrees Celsius, which is excellent for driving out everything present and rather poor at keeping large molecules intact. Big molecules shatter into small fragments at those temperatures, and the fragments are ambiguous. So a different protocol was designed, a lower peak temperature, held for longer, intended to coax heavier molecules out whole, rather than break them apart on the way. That protocol was applied to the 12-year-old Cumberland sample. The results were announced in 2025. The instrument detected 3 long-chain alkanes. Decane, with 10 carbon atoms in a row. Undecane, with 11. Dodecane, with 12. They are the largest organic molecules ever detected on Mars, by a wide margin, and they were found in rock deposited in a lake. The word organic here needs care, because it does the opposite of what most people expect. In chemistry, organic simply means carbon-based and does not imply biology at all. Meteorites contain organic molecules. Interstellar clouds contain organic molecules. The distinction that matters is not whether carbon compounds are present, but which carbon compounds, at what sizes, in what patterns. Which is why chain length is the interesting part. On Earth, straight-chain hydrocarbons of 10 to 12 carbons found in sediment are, most commonly, the breakdown products of fatty acids. Fatty acids are the molecules that make cell membranes, the boundary that separates the inside of a living thing from the outside, and one of the few features shared by every organism on this planet. Under heat and time, a fatty acid loses a carbon and becomes an alkane 1 carbon shorter. Undecanoic acid becomes decane. Dodecanoic acid becomes undecane. Tridecanoic acid becomes dodecane. The 3 molecules found at Cumberland correspond precisely to that progression from 3 fatty acids of adjacent length. On Earth, Fatty acids in that size range are overwhelmingly biological in origin. The team was careful, explicit, and public about the limit of that reasoning. Alkanes of this length also form without any life at all, through geological reactions between water and rock, and through the chemistry that produces organic molecules in meteorites and interstellar dust. The detection is not evidence of biology. It is evidence that Mars, 3.7 billion years ago, was doing organic chemistry of a complexity nobody had confirmed before. The abiotic baseline is not hypothetical either, and it is worth stating so the comparison is fair. Carbonaceous chondrite meteorites, primitive rocks that formed at the birth of the solar system and never got hot, contain amino acids, long-chain hydrocarbons, and a great deal of complex organic chemistry, all of it produced without any biology whatsoever. The Murchison meteorite, which fell in Australia in 1969, has yielded thousands of distinct organic compounds. So the universe manufactures this material readily. The question at Cumberland has never been whether organic chemistry can happen without life. It is whether this particular pattern of it did. The record before this was already substantial and worth stacking up. In 2018, the same instrument reported thiophenes and aromatic compounds in Gale mudstone. Thiophenes contain sulfur, and on Earth they are associated with the preservation of organic matter in sulfur-rich sediments. Sulfur chemistry acts as a preservative, locking organic molecules into forms that survive burial. Curiosity has also repeatedly measured chlorobenzene and various chlorinated compounds, which brings up a problem worth naming. Martian soil contains perchlorates, as the previous entries established. When a sample containing both perchlorate and organic molecules is heated, the perchlorate releases oxygen and chlorine and attacks the organics, destroying some and chlorinating others. So an instrument that works by heating is partially destroying the very molecules it is looking for and converting the survivors into chlorinated versions of themselves. Every organic detection at Gale has had to be interpreted through that filter. There is one more result that belongs here. In 2022, analysis of carbon isotope ratios in Gale samples found values in a range that on Earth would indicate biological processing. Living things preferentially take up the lighter carbon isotope, leaving a measurable signature. That same range, however, is also produced by ultraviolet degradation of atmospheric carbon dioxide, and also by the deposition of carbon from an interstellar dust cloud the solar system may have passed through hundreds of millions of years ago. 3 explanations. No way to choose between them with the instruments available. The quantities involved deserve mention because they are tiny. The alkanes were present at concentrations measured in parts per billion, a handful of molecules among thousands of millions. Detecting them at all required concentrating the released gas, separating the components by pushing them through a long column where different molecules travel at different speeds, and then weighing each fragment by its mass. The whole apparatus fits inside a rover the size of a small car, was built before 2011, and performed a measurement in 2025 that nobody had designed it to perform. The most surprising thing about the alkanes was not that they were found. It was that they were still there to find. Cosmic radiation degrades organic compounds in the upper meter of Martian rock, pulling chains apart over timescales of hundreds of millions of years. Mars has no magnetic field and effectively no atmospheric shielding, so this proceeds continuously. Finding intact 12 carbon chains in a sample drilled from about 5 centimeters below the surface was not what the models predicted. Either the destruction rate has been overestimated or the rock protected them better than expected, perhaps the sulfur chemistry, perhaps the mineral matrix, perhaps a recent exposure history that started the clock late. And either way, the implication runs in the same direction. If molecules of this size survived at 5 centimeters, then what is preserved at 2 meters, where the radiation cannot reach, is likely to be considerably better. That is the thought to carry into the rest of this list. What remains open is origin, and it will stay open. Distinguishing biological alkanes from geological ones requires measuring the isotopic composition of individual molecules, separating each compound and weighing its carbon atom by atom. No instrument on Mars can do that. The instruments that can are in laboratories on Earth, and they are the size of rooms. Chemistry that could have come from life is not the same thing as life. 50 years ago, one experiment claimed to have found the second thing. Number 9. The Viking result: nobody has retracted. On the 20th of July 1976, the Viking 1 lander touched down in Planitia. 6 weeks later, on the 3rd of September, Viking 2 came down in Utopia Planitia, 4,000 kilometers away. Each carried 3 biology experiments, and between them, they represented the most expensive, most carefully designed search for life ever attempted by anyone. 50 years later, one of those experiments has still not been explained. The labeled release experiment was designed by a scientist named Gilbert Levin, and the design was elegant in the way that good experiments are. It asked a question that could only be answered one way. A scoop of Martian soil was delivered into a small chamber. A nutrient solution was dripped onto it, a mixture of simple organic compounds that the team informally called chicken soup, chosen because almost anything alive on Earth can eat at least one of them. The crucial detail is that the carbon atoms in those nutrients had been replaced with carbon-14, which is radioactive. If anything in the soil consumed the nutrients and respired, it would exhale carbon dioxide containing that radioactive carbon, and a detector above the chamber would count it. And there was a control, which is what makes it an experiment rather than an observation. A second sample of the same soil would be heated first to 160 degrees Celsius, hot enough to sterilize anything living, and then given the same nutrients. If the response was biological, it would appear in the fresh sample and vanish in the cooked one. If the response was chemical, heat would not stop it. That is precisely what happened. The fresh sample produced a rapid, strong release of radioactive gas. The count rate climbed steeply, then leveled off, in a curve that looked like a population consuming a food supply and reaching a limit. It is worth standing inside that moment, because it is the closest anyone has ever come. It is the summer of 1976. The lander sits on a rust-colored plain scattered with boulders, its arm extended, and a small quantity of Planitia soil has just been delivered into a sealed chamber the size of a coffee cup. A valve opens. A measured drop of nutrient solution falls onto the soil. Then the chamber is closed, and a detector begins counting. On Earth, in a room in California, the numbers begin arriving. They arrive slowly, because the round trip takes minutes, and the data comes back in a thin stream shared with everything else the spacecraft is doing. The count rate is climbing. It is not drifting upward the way an instrument warming up would drift. It is rising steeply and steadily, in the shape the test was designed to produce if something in that soil was eating. The people in that room have spent years building this. They have a control sample scheduled, and the control has not run yet, and until it does, there is no way to know. Nobody in that room has yet seen the mass spectrometer result. For a stretch of days in the summer of 1976, the only data anyone had said that something on Mars had just taken a breath. The heat-sterilized control produced nothing at all. And then the result was reproduced at the second landing site, 4,000 kilometers away on different soil, by a different lander. By the criteria the experiment had published in advance, criteria written before launch, precisely so that nobody could move the goalposts afterwards. That was a positive detection of biological activity. It was overruled by a different instrument on the same spacecraft. Each lander also carried a gas chromatograph mass spectrometer, whose job was to identify organic molecules in the soil. It heated soil samples and analyzed the vapors, and it found essentially nothing. No organic compounds above a detection limit in the parts per billion range. That was the problem, and on its face it was decisive. Soil containing enough metabolizing organisms to produce the labeled release signal should also contain their remains, their waste, and the organic material they were made of. Even soil with no life in it at all should contain organic molecules delivered by meteorites, which fall on Mars as they fall everywhere. Finding no organics whatsoever was stranger than finding none of the biology. Faced with a positive biology result and a null chemistry result, the mission concluded that some unknown oxidizing chemical in the Martian soil had mimicked the effects of metabolism. The official verdict became inconclusive, leaning negative, and the world moved on. Gilbert Levin did not. He disputed that conclusion publicly for the rest of his life, in papers and interviews and conference talks, for 45 years. He published a paper as late as 2016, restating the biological interpretation. He died in July 2021, still holding the position that the experiment he had built had detected life on Mars. The other two biology experiments should be mentioned, because the labeled release did not stand alone. The pyrolytic release experiment tested whether anything in the soil could take up carbon from the Martian atmosphere and returned a small, ambiguous signal that nobody could call either way. The gas exchange experiment watched for changes in the gases above a moistened sample and returned a burst of oxygen so rapid and so large that it was immediately attributed to chemistry rather than biology, and that oxygen burst, incidentally, was one of the earliest clues that Martian soil contained something strongly oxidizing, 3 decades before anyone identified perchlorate. It is worth being fair to both sides here, because the arguments against him were not careless, and some of them are strong. The most telling is this. When a second dose of nutrient was injected into a sample that had already reacted, the signal did not rise again. It partially decreased. A growing population given more food should respond by producing more gas. A chemical reagent that has been consumed should produce less. That result is difficult to reconcile with biology and easy to reconcile with chemistry, and it remains the single strongest objection. There were others. Storing a sample in the dark at around 10 degrees Celsius for 2 months reduced the response substantially, which fits a decaying chemical as readily as a dying culture. And no organic molecules were found, which was the whole basis of the original dismissal. Then, in 2008, that last point changed. The Phoenix lander, sitting near the Martian North Pole, analyzed the soil and found perchlorate salts at around 0.5% by weight. This was a genuine discovery about Martian soil chemistry, and its implications for Viking were immediate and severe. Perchlorates are stable at room temperature and strongly oxidizing when heated. The Viking mass spectrometer worked by heating soil to several hundred degrees. Reanalysis showed that perchlorate at Martian concentrations, heated with organic material present, would destroy most of the organics during the heating step and convert some of the survivors into chlorinated compounds. And the Viking instrument had detected chlorinated compounds. Specifically, it had detected chloromethane and dichloromethane, and the team had attributed them to residual cleaning solvents used on the hardware before launch. That attribution was reasonable at the time. It is much less reasonable now, since curiosity has since found chlorobenzene and related compounds in Gale mudstone by exactly the same mechanism. So the chemistry result that overruled the biology result may have been an artifact of the instrument's own method. The mass spectrometer may have been destroying the evidence in the process of looking for it. That does not vindicate the labeled release result. It removes the strongest argument against it and leaves the question where it was in 1976, which is not the same thing as answering it. Perchlorate does not obviously reproduce the specific behavior of the labeled release curves, the shape of the release, the kinetics, the response to heating at intermediate temperatures. There is a much cited data point here. Sterilizing a sample at 50 degrees Celsius, too cool to kill most terrestrial microorganisms, but warm enough to affect some chemistry, produced an intermediate response rather than either extreme. Various non-biological explanations have been proposed over the decades. None has been demonstrated in the laboratory to reproduce all the features of the result. And here is the part that is genuinely hard to sit with. The experiment has never been repeated. Not once. In the 50 years since Viking, no lander sent to Mars by anyone has carried a metabolic life detection experiment. Every mission since has looked for habitability, for water, for organic molecules, for context, for the conditions that would make life possible rather than for life itself. Viking asked the question directly, got an answer nobody could interpret, and no one has asked it again. A man spent 45 years insisting that the experiment he built had found life on Mars. The strongest argument against him turned out to rest on an instrument that may have destroyed the evidence while looking for it. And because nobody ever sent the follow-up, he was never given the chance to be proved wrong either. Viking looked at soil. 20 years later, the argument moved to a rock that had come to us. Number 8. The Meteorite, from Allan Hills. On the 27th of December 1984, a team on snowmobiles working the Allan Hills ice field in Antarctica stopped to collect a greenish rock weighing about 1.9 kilograms. It was bagged, numbered, and shipped north, where it was catalogued as Allan Hills 84001. Then it sat in a collection for 9 years, misidentified. The Antarctic Meteorite program works because of an accident of geography. Dark rocks are conspicuous on blue ice, and the ice sheet flows slowly toward the coast, carrying anything embedded in it. Where the flow meets a barrier of buried mountains, the ice is forced upward and scoured away by wind, and whatever it was carrying is left concentrated on the surface. Certain stretches of Antarctic ice are, in effect, natural collection points where meteorites accumulate over tens of thousands of years. In 1993, the rock was re-examined and identified as Martian. That identification is not a matter of opinion, and the method behind it is worth explaining because it recurs in a later entry. Trapped inside some of these meteorites are tiny pockets of gas, sealed in during the impact that launched them. Analysis of those gases in 1983, on a different meteorite, found a composition matching the Martian atmosphere as measured directly by the Viking landers, the same proportions of nitrogen, argon, xenon, and the rest, and crucially, the same isotope ratios. Nothing else in the solar system carries that fingerprint. Once one meteorite was tied to Mars this way, the others could be matched to it by their oxygen isotope signatures. Allan Hills 84001 turned out to be exceptional even among Martian meteorites. It crystallized roughly 4.1 billion years ago, which makes it a piece of the ancient Martian crust, older than almost anything else available for study. It was blasted off the surface by an impact about 16 million years ago, drifted through the inner solar system, and fell on Antarctica roughly 13,000 years ago, where it lay in the ice until a snowmobile stopped beside it. There are now roughly 350 Martian meteorites identified on Earth, and they sort into a handful of families named after the stones that defined them: shergottites, knaclites, chassignites. Most are volcanic rocks between about 180 million and 600 million years old, which is to say they are young by Martian standards and tell us mainly about the planet's interior. Allan Hill's 84001 belongs to none of those families. It is an orthopyroxenite, a rock type essentially unique among the collection, and it is around 4 billion years older than most of the others. It is, in the most literal sense, a sample of the Mars this entire list is about, the old, wet Mars, delivered to Antarctica free of charge. On the 7th of August 1996, a team led by David McKay at the Johnson Space Center announced that this rock contained evidence of ancient Martian life. The announcement was made at a press conference, and the President of the United States addressed the nation about it the same day. For a period of weeks, a very large number of people believed the oldest question had just been answered. The case rested on 4 independent lines of evidence, and their strength was in the combination rather than in any single one. The first was carbonate globules, rounded deposits about 200 micrometers across, with alternating iron-rich and magnesium-rich zones, which on Earth are typically produced in water at low temperature and are sometimes associated with microbial activity. The second was organic molecules. Polycyclic aromatic hydrocarbons were found concentrated near the carbonate globules rather than distributed evenly through the rock, which is what you would expect if they were associated with whatever produced the carbonates. The third was the magnetite. Inside the carbonate rims were crystals of magnetite of a particular size, shape, and chemical purity. On Earth, magnetite crystals with those exact specifications are produced almost exclusively by magnetotactic bacteria, organisms that manufacture tiny magnets internally in order to orient themselves along the planet's magnetic field. At the time of the announcement, no non-biological process was known that produced magnetite matching that description. The fourth was the one that made the photographs. Electron microscopy showed elongated, segmented structures, tens to hundreds of nanometers long, sitting on the carbonate surfaces. They looked like fossilized microorganisms. That image ran on front pages worldwide. It is worth being clear that the team did not overclaim in print. The paper laid out the 4 lines of evidence, stated that each had non-biological explanations available, and argued that taken together, they were more consistent with ancient biological activity than with any single alternative. That is a careful sentence. It is not the sentence that reached the public, and it is not the sentence that a press conference and a presidential statement produce. The gap between what was written and what was heard is one of the more instructive things about this episode, and every entry on this list has some version of it. The counter-arguments began arriving within a year and have accumulated for 3 decades. The size problem came first. The segmented structures are roughly 100 times smaller by volume than typical terrestrial bacteria, small enough that fitting the machinery a cell requires inside them becomes very difficult. And at least some of the structures were shown to be artifacts of the preparation process itself. Samples for electron microscopy are coated with a thin layer of gold and palladium to make them conductive, and that coating forms its own textures, which at high magnification can look segmented. There is a further complication in that comparison. The terrestrial organisms invoked as the model for structures that small, sometimes called nanobacteria, are themselves a contested category. Whether entities of that size can be independently living organisms at all has been argued about on this planet, where samples can be cultured, sequenced, and handled directly, for as long as the Martian version has been argued about. The organics were argued to be terrestrial contamination. The rock had spent 13,000 years in Antarctic ice, and meltwater percolates. Polycyclic aromatic hydrocarbons are present in the Antarctic environment. Distinguishing molecules that arrived from Mars from molecules that arrived from the ice around it is genuinely difficult. The magnetite argument turned on crystallography. At least one magnetite grain was found to be in good crystallographic alignment with the carbonate crystal hosting it. That alignment is very unlikely if a bacterium made the magnetite and then died and left it in place. It is expected if the magnetite grew directly out of the carbonate, which would require high temperature, and which would mean the whole assemblage formed in hot fluid rather than in a cool microbial environment. Estimates of the formation temperature of those carbonates, made by different groups using different methods, have ranged from near freezing to over 700 degrees Celsius. That spread is a fair summary of how difficult this rock has been. More recent work has offered a fully non-biological route for the whole assemblage: water reacting with rock, serpentinization and carbonation, the same family of reactions that produce methane, generating organic molecules and carbonates together without any biology involved. The strangest verified detail about this entry has nothing to do with the rock. The NASA administrator at the time later stated publicly that the 1996 announcement rescued the agency's Mars program and directed something on the order of several $1 billion over 5 years into planetary exploration and the research that supports it. The Mars program that produced Mars Global Surveyor, Mars Odyssey, Spirit and Opportunity, the Mars Reconnaissance Orbiter, Phoenix, Curiosity, Maven, Insight and Perseverance, the program that produced nearly every other entry on this list, exists in the form it does, partly because of a claim about a rock that most researchers now believe does not contain fossils. What remains open is narrower than the popular account suggests, and it should be stated precisely. No single alternative explanation accounts for all 4 lines of evidence at once. The contamination argument addresses the organics but not the magnetite. The crystallographic argument addresses some magnetite grains but not all of them. The coating artifact addresses some structures but not the carbonate zoning. A minority of the original team never withdrew the claim, and the specimen is still curated and still periodically re-examined with instruments that did not exist in 1996. The consensus is that the evidence is not compelling. The consensus is not that it has been disproved. Those are different statements, and the difference is the whole reason this entry sits at number 8 rather than being left out. That claim was tested for 30 years, hard, by people who wanted it to be true. The next one has never been tested at all. Number 7. The Xenon Anomaly. The Martian atmosphere contains xenon, and the xenon is wrong. Xenon is a noble gas. It does not react with anything, it does not get incorporated into minerals, it does not participate in chemistry at all. It simply sits in an atmosphere, inert, keeping a record. That makes it one of the most useful tracers in planetary science, because whatever happens to xenon happened physically rather than chemically. Xenon comes in several stable isotopes, and the relevant comparison here is between xenon 129 and xenon 132. The ratio between those two is known for the Sun, for Earth's atmosphere, and for primitive meteorites, which represent the raw material the solar system was assembled from. Those 3 references agree reasonably well with each other. Mars does not. The Martian ratio of xenon 129 to xenon 132 is substantially higher than any of them. This is not a marginal or disputed measurement. It was first seen by the Viking landers in 1976, confirmed in the trapped gases of Martian meteorites, and measured directly in situ by Curiosity's sample analysis at Mars Laboratory in 2013. 3 independent approaches, decades apart, agreeing. Mars has too much Xenon 129. It is worth noting how the measurement was made in 2013, because it is a nice piece of work. The rover pumped Martian air into its laboratory, chemically removed the reactive gases, the carbon dioxide, the nitrogen, the oxygen, and left behind only the noble gases, which will not react with anything. Then it measured what remained. That gave the first direct, in situ determination of the Martian xenon isotopes from the surface of the planet, and it matched what had been inferred from meteorites decades earlier. 2 completely different routes to the same number. Now, why that particular isotope matters. Xenon 129 is the decay product of iodine 129, a radioactive isotope with a half-life of about 16 million years. 16 million years is short on a solar system timescale, which means all the iodine 129 that existed at the formation of the planets decayed away within the first 100 million years or so, leaving Xenon 129 behind. It is a clock that ran once, early, and then stopped. Iodine 129 is now used routinely as a chronometer for the earliest events in the solar system. Because it decays away so quickly, the amount of Xenon 129 a body carries records how early that body formed and separated its interior. A planet that finished assembling and started outgassing within the first few tens of millions of years traps a different signature from one that took longer. Mars, it turns out, formed remarkably fast, which becomes relevant near the very end of this list. It also happens that Xenon 129 is produced abundantly by nuclear fission. That coincidence is the seed of the claim. Beginning in 2011, the physicist John Brandenburg argued that the Martian xenon signature was the residue of enormous nuclear detonations in the planet's past. He combined it with a second observation. Maps of the Martian surface made from orbit show elevated concentrations of thorium and potassium over a broad region, including Mare Acidalium, a northern lowland area adjacent to Cydonia. In his framing, the isotopic anomaly and the elemental concentration together indicated 2 very large fission events, and in his later published statements, he argued these were not natural in origin. The claim circulated widely and continues to. It is worth taking seriously enough to actually examine, which is what this entry is for. The mainstream explanation for the xenon requires no explosions at all, and it is the same process that has driven the last several entries on this list. Xenon 129 accumulated in the Martian interior early, from iodine that decayed within the first 100 million years of the solar system and was outgassed into the atmosphere by volcanism. So Mars started with a xenon inventory already enriched in that isotope relative to the solar reference. That part happens on Earth too. Then Mars lost its atmosphere. Atmospheric escape is mass selective, as the entry on heavy hydrogen established. Lighter particles escape more readily than heavier ones, so an atmosphere that has been leaking for 4 billion years becomes progressively enriched in its heavier components. Applied to xenon's isotopes, escape preferentially removes the lighter ones and leaves the atmosphere with a higher proportion of the heavier ones. Here is the part that settles it, and it is not about xenon at all. If the xenon anomaly stood alone, one strange isotope ratio, on one element, with no other oddities, it would be a genuine puzzle demanding an unusual explanation. It does not stand alone. Argon on Mars is fractionated the same way. The ratio of argon-36 to argon-38 is shifted toward the heavier isotope, in the direction and roughly the magnitude escape predicts. Carbon shows it. Nitrogen shows it. Hydrogen shows it most dramatically of all, in the deuterium enrichment that lets us weigh the vanished ocean. Every one of those elements has different chemistry. They condense at different temperatures, they behave differently in rock, and they have nothing in common except mass. The only thing that treats them all the same way is a process that sorts by weight, and that process is escape to space, running continuously for 4 billion years. An isolated anomaly invites an unusual explanation. A whole periodic table of anomalies, all pointing the same direction, is a signature of one ordinary process operating for a very long time. The thorium and potassium maps have a similarly ordinary reading. Those maps come from the gamma-ray spectrometer aboard Mars Odyssey, which entered orbit on the 24th of October, 2001, and began mapping the elemental composition of the upper surface from above. It works by detecting gamma rays emitted when cosmic rays strike the ground, each element producing its own characteristic energies. It was the instrument that first mapped hydrogen, meaning buried water ice, across enormous areas of Mars, which is one of the more consequential results in the planet's exploration. That instrument's hydrogen map deserves its own moment, because it changed the planet. Hydrogen in the near surface means water ice, and what Odyssey found was that enormous swathes of Mars poleward of about 60 degrees latitude have water ice within a meter of the surface, in some places within a few centimeters. The map came out in 2002, and it turned Mars from a world where water was a historical question into a world where water is a resource with an address. Phoenix was sent to one of the places that map identified and dug down and found exactly what the gamma rays had predicted from orbit. The thorium and potassium variations it found track the distribution of particular volcanic rock types and the sediment eroded from them. Thorium concentrations vary across Mars by about a factor of 3, which is comparable to the variation across Earth's continental crust. There are regions of Earth with markedly elevated natural radioactivity, parts of Brazil, of India, of Iran, and nothing has ever exploded in any of them. Radioactive elements concentrate in certain magmas as they crystallize. That is what those elements do. There is also no candidate mechanism. Earth does have one known natural fission site, the deposits at Oklo in Gabon, where about 1.7 billion years ago, groundwater moving through unusually rich uranium ore sustained fission reactions on and off for a few 100,000 years. It is a genuine natural reactor, and it left an unmistakable local isotopic signature in the ore body. Nothing resembling Oklo has been identified on Mars, and Oklo was a slow, self-regulating reaction, not a detonation. So the isotopic evidence does not support the nuclear interpretation. It supports something quieter and, in its way, more consequential. A planet steadily losing its air across 4 billion years, leaving the same fingerprint on every gas it had. And now the honest part, which is why this entry sits as high as number 7, rather than being dismissed alongside the face at Cydonia. The face was closed by pointing a better camera at it. 3 times, at increasing resolution, until the claim had nowhere left to stand. That worked because the claim was about a surface, and surfaces can be photographed. There is no equivalent instrument for the Martian subsurface. Nobody has drilled anywhere near Mare Acidalium. Nobody has drilled anywhere on Mars to any depth that would test a claim about the planet's past at all, as the final entry on this list will make uncomfortably specific. The Xenon claim can be answered on the isotopic evidence, and it is answered. The fractionation pattern across every gas in the atmosphere is not consistent with a detonation and is consistent with escape. But the broader category of claims about what might lie beneath the Martian surface cannot be closed the way Cydonia was closed, because the tool that would close them has never been sent. That is not a defense of any particular claim. It is a description of the state of the evidence, and it is the shape of the problem that the last few entries on this list are really about. That whole argument depends on a planet that lost its atmosphere. The next entry is about the day it started losing it. Number 6. The magnetic stripes of a dead world. Mars has no magnetic field. A compass taken to the surface would wander uselessly. There is no north to find, because there is no global field to define one. Mars is, magnetically speaking, a dead planet. The rocks remember otherwise. Mars Global Surveyor entered orbit in September 1997, and it arrived on a long, slow schedule. Rather than firing engines to circularize its orbit, it used a technique called aerobraking, dipping repeatedly into the top of the Martian atmosphere and letting drag do the work, over hundreds of passes across many months. That saved an enormous amount of fuel. It also carried the spacecraft far lower than a science orbit normally goes, again and again with its instruments running. That spacecraft story has a coda worth mentioning. Mars Global Surveyor operated for 9 years, mapped the planet's topography, photographed Cydonia twice at high resolution, discovered the crustal magnetism, and imaged gullies and dust devil tracks and the changing polar caps. Contact was lost in November 2006 after a software update left a solar array pointing incorrectly and the spacecraft's battery overheated. It had been sending data for more than 4 times its planned mission. Almost every entry on this list from the late 1990s onward rests on something it measured. One of those instruments was a magnetometer, and on those low passes it measured something nobody had predicted. The ancient southern highland crust is magnetized. Intensely. In places, the magnetization is around 30 times stronger than anything measured over Earth's crust, field strengths reaching roughly 1500 nanotesla at satellite altitude, in a planet whose global field is 0. A word on the scale of that measurement, because the raw number is easy to misread. 1500 nanotesla sounds small next to Earth's surface field of about 50,000 nanotesla. But Earth's field is generated by a core 3,000 kilometers beneath your feet and fills the whole planet. The Martian value is what a magnetometer reads from 100 kilometers above the ground, produced by nothing but rock that cooled 4 billion years ago and has been sitting there ever since. Measured at the surface, over the strongest patches, the field would be a substantial fraction of what a compass feels on Earth, generated entirely by memory. And it is not uniform. It is banded. The magnetized regions, concentrated in areas called Terra Cimmeria and Terra Serenum, are arranged in alternating stripes of opposite polarity. They run roughly east to west. Some are 2,000 kilometers long and 200 kilometers wide. The results were reported by Mario Acuna, Jack Connolly, and their colleagues, and the pattern they published looked immediately familiar to anyone who had studied Earth's ocean floor. On Earth, striped crustal magnetism is one of the founding pieces of evidence for plate tectonics. New crust forms at a mid-ocean ridge, cools, and as it cools past a certain temperature, it locks in the direction of the planetary magnetic field at that moment. The seafloor spreads outward. The planetary field reverses periodically. Earth's has done so hundreds of times, most recently about 780,000 years ago. So the seafloor becomes a magnetic tape recording, with stripes of alternating polarity spreading symmetrically away from the ridge. Whether Mars ever had plate tectonics is genuinely disputed, and the stripes alone do not settle it. Other mechanisms can produce banded magnetization. What the stripes do settle, beyond dispute, is bigger than that. They establish that Mars once had a global magnetic field generated by a dynamo, a convecting, electrically conducting molten core, churning, generating a field the way Earth's does now. They establish that the field was strong. Estimates from magnetized Martian meteorites put the ancient field's intensity at something comparable to Earth's present field. And the alternating polarity establishes that it reversed, repeatedly, which is what a working dynamo does. Mars was, once, a planet with a magnetosphere. The timing is the part that matters for everything else on this list, and it can be read directly off the map. The magnetized crust is the oldest crust, and the great impact basins, Hellas, Argaea, Isidis, are essentially unmagnetized. Hellas alone is about 2,300 kilometers across and 7 kilometers deep, the scar of a collision that melted an enormous volume of rock. If the dynamo had been running when that impact occurred, the rock that cooled afterwards would have locked in the field. It did not. Those basins formed roughly 4 billion years ago, so the dynamo had already stopped by then. Mars had a magnetic field for perhaps the first 500 million years of its existence, and then lost it. It is worth being clear about what a dynamo actually requires, because the conditions are surprisingly specific. You need a large volume of electrically conducting fluid, molten iron, in a rocky planet's case. You need that fluid to be convecting, which means heat has to be escaping from the core into the mantle fast enough to keep it stirring. And you need rotation, which organizes the convection into columns that reinforce each other rather than cancelling out. Remove any one of the three, and the field collapses. Mars has plenty of iron and rotates at almost exactly Earth's rate. A Martian day is 24 hours and 39 minutes. What it ran out of was the heat flow. The most likely reason is size. Mars is about half Earth's diameter and roughly a ninth of its mass. A smaller body has proportionally more surface area relative to its volume, so it radiates its internal heat away faster. The Martian core cooled, convection slowed, and the dynamo shut down. Mars's core is also thought to contain a high fraction of sulfur, which lowers its melting point and changes how it solidifies, though the details remain unsettled. InSight measured the core directly from seismic waves reflecting off the core mantle boundary and found a liquid core about 1,800 kilometers in radius, larger and less dense than most models had expected. That result sharpened the question rather than answering it. What followed the shutdown is the causal chain that defines the planet, and it is worth laying out in order because it ties this entire list together. The field went. With no global magnetosphere deflecting it, the solar wind reached the upper atmosphere directly and began stripping ions away, the process MAVEN now measures in real time, storm by storm. As the atmosphere thinned, surface pressure fell. As pressure fell toward the triple point of water, liquid water at the surface became unstable, boiling and freezing at once. As surface water disappeared, chemical weathering stopped, and the clay-forming reactions that had been locking water into the crust wound down. The rivers stopped running. The lakes dried and did not refill. The shorelines were left behind at the elevations where the water had last stood. Every entry on this list about vanished water is downstream of this entry. The window closed here. There is a detail about the aftermath that is quietly remarkable. The old field is gone as a global structure, but the strongest magnetized patches are still strong enough to matter. Above them, small localized magnetospheres form, deflecting the solar wind on scales of a few hundred kilometers. And where charged particles are funneled into the atmosphere along those local field lines, they produce aurorae, discrete, patchy aurorae, tied to spots of ancient crust rather than to any global field, first detected by Mars Express in 2005. So there are places on Mars where the sky glows because of a magnetic field that stopped working 4 billion years ago. The rock is still holding the shape of it. What remains open is a set of real questions. Why the dynamo stopped when it did, rather than 100 million years earlier or later? Whether it ever restarted briefly, as some magnetized younger terrain hints. Whether Mars had plate tectonics at all, or whether the stripes formed some other way. And what the timing means for the origin of life, since the field was running during precisely the period when Mars was warmest and wettest, which is a thread the last few entries will pick up. The reason Mars is a desert is that its core cooled early. Which is a way of saying that the difference between a living world and a dead one can come down to how big it was when it formed. When the air thinned, the dust began to move. It has been burying the planet ever since. Number 5. The deposit the size of India. Along the Martian equator, straddling the boundary between the ancient highlands and the northern lowlands, lies a deposit that has no equivalent anywhere else in the inner solar system. It is called the Medusae Fossae Formation, and its dimensions are difficult to take in at first hearing. It stretches discontinuously for more than 5,000 kilometers. Its total area is comparable to India. It is the largest sedimentary deposit on the planet by a wide margin, and it is soft enough that the wind has carved it into fields of parallel ridges running for tens of kilometers, some of them hundreds of meters tall. The yardangs are worth a moment on their own because they are the visual signature of the place. Wind blowing consistently from one direction, carrying sand along the ground for millions of years, does not scour a surface evenly. It cuts grooves, and the grooves deepen, and what is left between them are long parallel ridges aligned with the wind, tapered like the hulls of upturned boats. In the Medusae Fossae Formation, these run for 10 kilometers and more, in sets so regular and so extensive that when they were first mapped from orbit, the pattern looked more like an instrument artifact than like terrain. That regularity is what soft rock and a steady wind produce, given enough time, and it is one of the more genuinely beautiful landscapes in the solar system. For decades, what it was made of was genuinely unknown. The problem was that the formation behaves oddly under radar. It is far more transparent to radio waves than ordinary rock, and its bulk density is low. Two candidate explanations dominated. The first was volcanic ash, an enormous accumulation of fine pyroclastic material, deposited by eruptions of a scale that has no terrestrial parallel, and porous enough to explain the radar behavior. The second was ice, a deposit of dusty water ice, which is also radar transparent and also low in density. Those are very different histories, and for 30 years the data could not distinguish between them. In January 2024, an analysis of Marsis radar soundings from Mars Express reported a result. The deposits reach up to 3.7 kilometers thick, considerably more than earlier estimates. And the internal reflections, the boundaries the radar detects within the deposit, alternate in a pattern of ice-rich and ice-poor layers that closely resembles the layered polar deposits at the Martian poles, where the ice interpretation is not in doubt. If that reading holds, the implication is substantial. The Medusae Fossae Formation would contain the largest reservoir of water anywhere on Mars outside the polar caps. Melted and spread evenly over the whole planet, the ice in it would form a global layer somewhere between 1.5 and 2.7 meters deep. It is worth putting that thickness against something familiar. 3.7 kilometers is deeper than the Grand Canyon, which reaches about 1.8 kilometers at its deepest. So the Medusae-Fossae formation is roughly 2 Grand Canyons of loose material stacked on top of each other, spread across an area the size of India. If you stood on the top of it and dug straight down, you would pass through more vertical distance than any borehole ever drilled on Earth's continents managed for its first 2 decades of effort, and you would still be inside the deposit. And it is at the equator. That location matters enormously for anything that ever goes there. The equator is where landing is easiest, where temperatures are highest, where solar power works best, and where every crude mission architecture wants to be. Water ice at high latitude is abundant and awkward to reach. Water ice at the equator, buried beneath a few hundred meters of dry dust that has insulated it from sublimating away, is a different proposition entirely. The formation has a second role, and it is the one every mission has felt. It is thought to be the single largest source of the dust that coats the entire planet. Mars is not fundamentally red so much as covered in red, a fine, iron oxide-rich dust with grains around 3 micrometers across, small enough to stay suspended in the thin atmosphere for months once lifted. Global storms redistribute it across every surface on the planet. Those storms follow a rough rhythm. Planet-encircling dust events occur every 3 to 4 Martian years, every 5 or 6 Earth years, and they can raise dust to altitudes of 60 kilometers and keep the whole atmosphere opaque for weeks. Smaller regional storms happen every year. Between them, the dust never really settles for long, and every surface on Mars is being resurfaced continuously by an extremely thin, extremely persistent snowfall of iron oxide. Every rover has driven through it. Every solar panel has been dimmed by it. It is why Opportunity's mission ended when the 2018 planet-encircling storm raised the atmospheric opacity high enough to block nearly all sunlight for weeks. It is why InSight's mission ended 4 years later, as accumulation on its panels slowly starved it of power. The formation that may hold the largest equatorial water reserve on Mars is also, in a real sense, what has killed most of the machines sent there. Now, the relevance of this entry to the question the list is asking, which requires no speculation at all. There is a region of Mars the size of a subcontinent, up to 3.5 kilometers deep, made of material soft enough to be carved by wind. It has been accumulating for an unknown length of time. It sits over terrain that was there before it, and that terrain is now underneath it, under hundreds of meters of dust in the shallowest places and kilometers in the deepest. Nothing has ever descended into it more than the top few centimeters. That sentence is going to recur, and it will get more precise as this list ends. But it is worth registering here, at an entry that is entirely uncontroversial. This is not a claim about what might be buried. It is a statement about what burial means on a planet where the wind has been depositing material for billions of years, and where no one has ever dug a hole deeper than a shoe. What remains open about the formation itself is most of it. Its age is poorly constrained, because its surface is young in crater count, and that reflects continuous erosion rather than recent deposition. The top is constantly being stripped away, resetting the clock. Its origin is unresolved, even under the ice interpretation, since a deposit of that size requires a mechanism for putting that much ice at the equator, which is not where ice is stable today. Mars's axial tilt wanders, and at high obliquity equatorial ice becomes plausible, so the formation may be the residue of a very different climate configuration. Nobody knows how many such configurations are recorded in it. And the ice interpretation itself is not universally accepted. It is the best current reading of the radar. Settling it would require a lander with a drill, or a radar operating at frequencies nothing at Mars currently uses. There is one more thing worth saying about this deposit, which is a matter of arithmetic rather than of theory. Mars has almost no erosion by water today and no plate tectonics recycling its crust. What lands on the surface tends to stay on the surface, get buried by what lands next, and remain. Earth destroys its own past continuously. Subduction consumes ocean floor, mountains rise and are worn flat, and rock older than about 4 billion years survives almost nowhere. Mars does not do that. Mars buries its past instead of destroying it, which means the record is still there. Whatever happened on the surface of Mars in its first billion years was not erased the way Earth erases things. It was covered over, layer by layer, and left. It is simply underneath. That is what is buried under the dust. The next entry is about what is under the rock. Number 4. The water that is still down there. The InSight lander touched down in Elysium Planitia on the 26th of November, 2018, and then it did almost nothing. That was the plan. InSight had no wheels. It was not sent to explore anything, and it never moved from the spot where it landed. Its entire purpose was to sit still and listen, because it carried a seismometer sensitive enough to detect ground motion smaller than the width of a hydrogen atom, and an instrument that sensitive cannot be dragged around. The seismometer was called CEIS, built by a French-led consortium, and it was placed on the ground by the lander's arm and then covered with a dome to shield it from wind and temperature swings. Then it listened. The expectation was modest. Mars was widely assumed to be geologically dead, a planet whose interior had cooled, whose volcanoes had stopped, whose crust had long since stopped moving. Some seismic activity from thermal contraction and meteorite impacts was expected. Not much. Over 4 years, it recorded more than 1,300 seismic events. Mars is not dead. It is quietly and persistently active, and it has been the whole time, and nobody knew because nobody had ever put an instrument down and waited. A large fraction of the strongest quakes traced back to a single place. Cerberus fossae is a set of parallel fractures running for 1,000 kilometers or more across Elysium Planitia, cutting through terrain so young, by crater counting, that it must have formed within the last few million years. Some of those fractures show evidence of both recent volcanism and recent water outflow. Cerberus fossae is a fault system that is still moving on a planet that was supposed to have finished. Most Marsquakes are small. Magnitudes cluster between 2 and 4, which on Earth would be barely noticed. They are detectable because Mars is seismically quiet. No oceans, no weather to speak of, no traffic, no industry. An instrument on Mars is listening in a silence that no seismometer on Earth ever experiences. Then came the 4th of May, 2022. The event catalogued as S1222A registered magnitude 4.7. That does not sound large, and by terrestrial standards, it is not. But seismic magnitude is logarithmic, and the energy released by that single event was comparable to every other Marsquake in the entire 4-year catalogue combined. It rang the planet for something on the order of 10 hours. Waves from a quake that size do not simply travel from source to receiver and stop. They travel through the interior, they refract off the core, they run around the surface, they come back around the far side and pass the instrument again. For most of a Martian day, the seismometer in Elysium Planitia was recording a planet still vibrating from a single event. It is worth following that event as it arrived, because it is the closest anyone has come to hearing another planet. The instrument sits under its dome on a flat plain, shielded from the wind, recording nothing in particular. 2,200 kilometers away, 20 kilometers underground. A fault slips. The first thing to arrive is the compressional wave, the fastest kind, a pulse of alternating squeeze and stretch traveling straight through the rock. It reaches the seismometer minutes later as a small, sharp arrival. Then, some minutes after that, the shear waves. These travel more slowly and shake the ground sideways, and the delay between the two arrivals is what gives away the distance. Every seismologist reads that gap first. Then the surface waves, which are slower still and much larger, running around the curve of the planet rather than through it. They pass the lander, keep going, cross the far side of Mars, and come back around, weaker, and pass again. And again. The ground does not stop moving. For hours the trace keeps writing, a long, decaying oscillation as the energy circulates and slowly bleeds away into heat. 10 hours of it. A planet that everyone had described as dead, sounding, for the better part of a Martian day, like a struck bell. The immediate question was what had caused it. A meteorite impact was the obvious candidate, and it was testable. A strike large enough to produce that signal would leave a fresh crater. So every orbiter at Mars was brought into a coordinated search of the plausible region. They found nothing. No new crater anywhere along the track. That left a tectonic source. Analysis placed the epicenter about 2,200 kilometers from the lander, in southern Elysium Planitia, near the dichotomy boundary, and against first expectations, outside the Cerberus Fossae region that had produced most of the other large events. The best-fitting solution is slip on a fault in the mid-crust, somewhere around 18 to 28 kilometers deep. Something moved, 20 kilometers down, in a place nobody had flagged, hard enough to ring the planet for 10 hours. Impacts turned out to be useful, rather than merely noisy. On several occasions, the seismometer recorded an event, and orbital imaging afterwards located a fresh crater exactly where the seismic solution had predicted. New dark blast patterns on the surface, sometimes with ice excavated from below and thrown across the ground around them. Each of those pairings calibrated the network. A known source at a known distance is the best gift a seismologist can receive, and Mars supplied several. The seismic data also settled some long-standing questions about the planet's structure. The crust is between about 20 and 72 kilometers thick, depending on where you measure. The core is liquid and about 1,800 kilometers in radius, larger than models had predicted and less dense, which implies a significant fraction of lighter elements mixed in with the iron. The mission ended on the 15th of December, 2022, and it ended in the way most Martian missions end. Dust accumulated on the solar panels month after month, and no wind came to clear it. Power fell steadily until there was not enough to run the seismometer, and then not enough to transmit. The last image the lander sent was of the instrument sitting on the ground under its dome, exactly where the arm had set it down 4 years earlier. But the most consequential result came after the mission had ended. A reanalysis published in 2024 took a different approach to the same seismic data. Rather than looking at individual events, it examined how seismic wave speeds vary with depth through the Martian crust, and asked what combination of rock and pore-filling material would produce the observed profile. Between roughly 11.5 and 20 kilometers down, the best fit is fractured igneous rock, whose pore spaces are saturated with liquid water. The volume implied, if that interpretation extends across the planet, is difficult to state casually. Extracted and spread over the surface, it would form an ocean between 1 and 2 kilometers deep. That would make it, by a very wide margin, the largest water reservoir on Mars. More than the polar caps. more than the equatorial deposits. More, in fact, than all of Earth's lakes and rivers combined. And it would be, by the standards of this planet, a habitable environment. That is not a rhetorical stretch. Earth has a deep subsurface biosphere, microbial communities living in the pore spaces of rock kilometers beneath the surface, with no sunlight, no oxygen, and no connection to the surface ecosystem, running on chemical energy from water-rock reactions. Estimates put a substantial fraction of this planet's total microbial biomass down there. Those organisms live in exactly the setting the Martian seismic data describes: fractured rock, saturated with water, warm from the planet's residual heat, chemically active. If Mars had life at the surface when the surface was wet, and the surface then became uninhabitable over hundreds of millions of years, the deep crust is precisely where it would have retreated to. Not as an escape, nothing chooses this, but as the last place where the conditions never changed. What remains open is whether the seismic interpretation is unique, and here caution is warranted. Other pore-filling materials and other crustal compositions can produce similar wave speeds. The measurement comes from one instrument at one location on a planet with as much land area as Earth, and extrapolating it globally is a substantial assumption. The authors said as much. And reaching it is not a near prospect. 12 kilometers is deeper than all but a handful of boreholes ever drilled on Earth, and those took years, enormous rigs, and continuous power. Nothing remotely capable of that has ever been flown anywhere. InSight's own experience makes the point better than any argument. It carried a self-hammering probe, nicknamed the Mole, designed to bury itself 5 meters into the Martian soil to measure heat flow. It got about 35 centimeters down. The soil would not give it the friction it needed to push against, so it bounced in place, and after 2 years of attempts, the team gave up. 5 meters was the goal. 35 centimeters was the result. There may be more liquid water on Mars right now than in all of Earth's rivers and lakes together. The next entry is about the traffic between the two planets. Number 3. The rocks. The two planets trade. There are pieces of Mars in museums on Earth. Roughly 350 of them have been identified, and anyone can go and look at one. That fact is strange enough on its own that it is worth establishing carefully, because the identification is not a matter of inference or of style. It is a direct chemical match. In 1983, researchers analyzed gas trapped inside tiny glass pockets in a meteorite catalogued as ETA 79001, found in Antarctica. The glass had formed when a shock wave melted part of the rock, and it cooled quickly, sealing whatever atmosphere was present at that moment inside it. The composition of that trapped gas, the proportions of nitrogen, argon, carbon dioxide, neon, xenon, and crucially, the isotope ratios of each, matched the Martian atmosphere as measured directly by the Viking landers 7 years earlier. Nothing else in the solar system carries that fingerprint. The Martian atmosphere is distinctive precisely because of the 4 billion years of escape fractionation discussed several entries ago. It is, in effect, a signature that cannot be forged. Once one meteorite had been tied to Mars this way, the rest could be matched to it through their oxygen isotope compositions, which vary systematically between the bodies of the solar system and which serve as a reliable address for where a rock formed. The families these rocks sort into are named after the stones that defined them, and the naming is charmingly unsystematic. Shergottites are named for a meteorite that fell at Shergoti in India in 1865. Nakhlites are named for the Nakhla meteorite, which fell in Egypt on the 28th of June 1911, and which is one of the very few Martian meteorites actually observed arriving, Witnesses reported around 40 stones falling, and one local account claims a dog was struck, though no remains were ever produced, and the story has the shape of a story. Chassagnites take their name from a stone that fell in France in 1815. 3 fragments of Mars, landing in 3 countries, in 3 centuries, decades before anyone knew there was a Mars to fall from. The delivery mechanism is straightforward, and unlike much on this list, it is not disputed by anyone. A large impact on Mars accelerates surface rock upward. Some fraction of the ejected material exceeds the planet's escape velocity, which is about 5 kilometers per second, roughly 45% of Earth's. That difference matters enormously, because the energy required scales with the square of velocity. Launching rock off Mars is far easier than launching it off Earth, and the thin atmosphere means there is very little to slow the fragments on the way out. Once free, the fragments enter their own orbits around the Sun. Most of them stay there indefinitely. A small fraction have orbits that eventually intersect Earth's, and a fraction of those arrive. The transit times can be measured, which is a satisfying detail. While a fragment is in space, unshielded, cosmic rays strike it and produce distinctive isotopes at a known rate. Measuring those isotopes gives the exposure age, how long the rock was in space. Martian meteorites come back with exposure ages ranging from a few 100,000 years to about 20 million. Those ages cluster into groups rather than spreading evenly, which tells us something else. The whole collection on Earth comes from perhaps 10 separate impact events on Mars, not from a continuous drizzle. Only about 10 craters on Mars are considered viable candidates for having launched them. Now the part that reorients the question this list has been asking. The exchange runs both ways, and it always has. Impact ejector modeling indicates that Earth has delivered material to Mars in quantities that are comparable to and probably greater than the reverse. There is more Earth to eject. Earth's higher escape velocity makes it harder, but the impacts that hit Earth are on average larger and more energetic, and Mars, though a smaller target, is reachable. Over the first billion years of the solar system, when the impact rate was orders of magnitude higher than it is now, the 2 planets exchanged material in quantities best measured in billions of tons. The numbers on the Earth to Mars direction deserve a moment, because they are rarely stated. During the heavy bombardment, when the inner solar system was still being pounded by leftover debris, a single large impact on Earth could loft millions of tons of surface rock past escape velocity. Some fraction of that material would reach Mars over the following millions of years. Integrated across the whole bombardment era, the total delivery is estimated in the billions of tons, which, if Earth's earliest microbial ecosystems were established by then, means that fossil traces of early Earth life may be sitting in Martian sediment right now, in a rock nobody has ever turned over. And during exactly that period, both of them were wet. This is the reason the entry sits at number 3. If life arose on either planet during the era when both had liquid water, the exchange is a demonstrated physical route by which it could have reached the other. Nobody needs to propose a mechanism. The mechanism has been running continuously for 4.5 billion years, and there are samples of it in display cases. The timing is not symmetric, and that asymmetry is the whole point. Mars is smaller, so it cooled faster. It had a solid crust earlier. It had liquid water earlier. It had a magnetic field protecting that water while Earth was still being resurfaced by giant impacts, including the one that formed the Moon and left this planet's surface molten. Whatever order things happened in, Mars reached the state of being a stable, wet, protected world before Earth did. The survivability question has been tested rather than assumed, which is unusual for a topic that attracts speculation. Laboratory experiments have subjected bacterial spores and hardy microorganisms to the shock pressures characteristic of impact ejection, and a fraction survive. Others have exposed organisms to prolonged vacuum, to the temperature range of interplanetary space, and to radiation doses corresponding to millions of years of transit, and again, a fraction survive, particularly if shielded inside rock more than a few tens of centimeters thick, which blocks the majority of cosmic radiation. The organisms usually used are bacillus spores, which survive almost anything, and Deinococcus radiodurans, which repairs radiation damage to its own genome with an efficiency that is difficult to believe until it is measured. Atmospheric entry is less of an obstacle than intuition suggests. A meteorite entering the atmosphere is heated ferociously on its outer surface, and that surface ablates away, carrying the heat with it. Rock is a poor conductor. The interior of a fist-sized stone can remain cool throughout the fall, which is why freshly fallen meteorites have sometimes been found with frost on them, having arrived carrying the cold of space in their centers. So the route is real, the transfer is documented, and the survival is demonstrated in the laboratory. There is an inversion buried in this that is worth stating plainly, because it is the version most people find unsettling. The usual framing of this list is whether something lived on Mars. But the transfer is two-way, and the ordering favors Mars, so the same physics supports a different question, whether the earliest chemistry that led to life here began there and arrived aboard a rock. That is not a claim, and there is no evidence for it. It is simply what the mechanism permits, and the mechanism is not speculative. What has never been observed is the event itself. Nothing living has ever been recovered from a Martian meteorite. Every claimed detection has resolved into contamination, artifact, or ambiguity, as the Allan Hills entry described in detail. But notice what this entry does to the shape of the question. If material has been moving between these two worlds since before either had a fossil record, then asking whether Mars had life and whether Earth had life are not fully separable questions. They are two ends of one system. And if life arose once, in one place, in a solar system where two adjacent planets were exchanging rock, then the question of where it started is not answered by where it is now. The two planets have been trading material since before either had anything worth calling a history. Which leaves one question, and it turns on which of them was ready first. Number 2. The world that was habitable first. In 2011, a dark and unusually heavy stone was recovered from the Sahara Desert in Morocco. It weighed about 320 grams. It was catalogued as Northwest Africa 7034, and because of its color and the small bright crystals scattered through it, someone gave it the nickname Black Beauty, which has stuck ever since. It turned out to be unlike any Martian meteorite anyone had seen. Almost every other Martian meteorite is a volcanic rock, solidified magma, telling us about the planet's interior, and mostly young. Black Beauty is a breccia. A breccia is not one rock, but many, fragments of older material, broken by impacts and then cemented back together into a new stone. It is Martian regolith, the shattered surface layer of the planet, compacted and preserved. A breccia is also, in a sense, a library rather than a book. Every fragment cemented into it is a separate sample of the Martian surface, from a separate place and a separate time, gathered up by impacts and bound together. Studying Black Beauty is not studying one rock. It is studying dozens, all of which happen to have arrived in the same package. That is why it has become, after the Allan Hills stone, the most intensively examined Martian meteorite in existence, and why a group of paired stones found in the same region of the Sahara are treated as pieces of the same original fall. That makes it the closest thing anyone has to a returned soil sample from Mars. It also contains roughly 10 times more water than any other Martian meteorite, around 6,000 parts per million, locked into its minerals. And inside it are zircons. Zircon is one of the most useful minerals in geology, and the reason is a quirk of its crystal chemistry. When zircon crystallizes out of a cooling magma, it readily accepts uranium atoms into its structure, and it strongly rejects lead. So a newly formed zircon contains uranium and essentially no lead. Uranium decays into lead at a rate that is known with great precision, and that nothing, not heat, not pressure, not chemistry, can alter. That means every zircon crystal is a clock that started the moment it formed. Measure the accumulated lead against the remaining uranium, and the crystal tells you its own age directly. Zircon is also extraordinarily durable. It survives erosion, burial, reheating and reworking, which is why zircons in a breccia can be far older than the breccia itself. The zircons in Black Beauty date from about 4.48 to 4.43 billion years ago. They are the oldest pieces of Mars that anyone has ever held. Older than any rock on Earth's surface. Older, by a considerable margin, than the oldest intact crust this planet has managed to keep. For scale, the solar system itself is about 4.57 billion years old. These crystals formed within roughly 100 million years of the Sun igniting, which, on the timescale this list has been working in, is almost immediately. Mars had already assembled itself, differentiated into core and mantle and crust, and cooled enough to crystallize minerals. Then, in 2024, a detailed study of a single grain took this considerably further. The grain in question dates to about 4.45 billion years ago. Researchers mapped the trace elements through its internal growth zones at nanometer scale, reading the crystal outward, ring by ring, the way you would read a tree. What they found in those zones were unusual concentrations of iron, aluminium, and sodium, distributed in a pattern that does not occur when a zircon grows in dry magma. It is the pattern left when a crystal grows in the presence of hot, mineral-bearing water. The technique deserves a moment of admiration on its own terms. A zircon crystal from another planet, recovered from a desert on this one, sectioned, polished, and then mapped at a scale of billionths of a meter to read the chemistry of the water it grew in 4.5 billion years ago. The crystal is smaller than a grain of sand. The measurement is of individual growth bands within it. And the answer concerns the surface conditions of a world at a moment when this one did not yet have a surface worth the name. The interpretation is hydrothermal. This crystal formed in or beside a hot water system, a hot spring, or a zone where circulating groundwater met warm rock, on or just below the surface of Mars, 4.5 billion years ago. Now set that date against Earth's. The impact that formed the Moon occurred somewhere around 4.5 billion years ago, and it left this planet with a global magma ocean. Earth's surface was molten. Any chemistry that had begun was erased entirely. Earth's oldest surviving mineral grains are the Jack Hill zircons of Western Australia, which date to about 4.4 billion years, and which are themselves taken as evidence that liquid water existed here by that time, read from their oxygen isotope ratios. The Martian hydrothermal zircon is older than that. It comes from a planet that had already cooled, crystallized a crust, and begun circulating hot water through it while Earth was still recovering from the collision that made the Moon. The head start is on the order of 50 to 100 million years. That sounds modest against 4.5 billion. It is not modest at all when the question is, which world had the conditions first? because for a substantial part of that interval, Earth did not merely lack those conditions. Earth had a surface that would have destroyed anything. There is a reason Mars was ready first, and it is the same reason it failed later. Mars is about 11% of Earth's mass. A smaller body loses its formation heat faster, so it solidifies sooner, crystallizes a crust sooner, and can hold liquid water on that crust sooner. The identical property that gave Mars its head start, being small, is what shut down its dynamo 500 million years later and cost it the atmosphere. The planet was quick to become habitable and quick to stop being habitable, and both facts follow from one number. And hydrothermal systems are not incidental to this question. They are close to the center of it. On Earth, hydrothermal environments are among the leading candidate settings for the origin of life. Hot springs and deep-sea vents bring together the four things that seem to be required: liquid water, a source of heat, mineral surfaces that can catalyze reactions and concentrate molecules, and chemical energy gradients that can be tapped. Serpentinization in such systems generates hydrogen, which is about the most usable chemical fuel there is, and which some of the oldest metabolisms on this planet still run on. Mars had all of that. It had it first, and it had it while the alternative was a magma ocean. It is also worth noting how tight the constraint on early Martian formation has become from a completely different direction. The iodine and xenon chronology from an earlier entry on this list, the isotope system that records how early a body separated its interior and began outgassing, independently indicates that Mars assembled remarkably fast, faster than Earth did, possibly within a few million years of the solar system's formation. Two entirely separate lines of evidence, one from a decayed isotope in an atmosphere and one from a crystal in a Saharan meteorite, agreeing that Mars got there first. Then Mars kept it. The rivers ran for something like 1 billion years. The lakes filled and dried and filled again. The crust circulated water through it. The magnetic field held for the first stretch of that, protecting the atmosphere that made it possible. What remains open is enormous and needs saying plainly rather than left implied. Having the conditions is not having the outcome. Nothing in Black Beauty is a biosignature. That zircon records hot water on early Mars, and nothing more. It does not indicate that anything used it, and there is no measurement anyone has made that would show that either way. What the crystal establishes is priority. If the origin of life is a matter of the right environment, plus enough time, then the first place in this solar system to have both was not this planet. That is the whole of the argument, and it is worth being precise about how far it goes. It does not say Mars had life. It says Mars had the opening, earlier, and held it open for a very long time. Mars had warm water first. Which leaves one question, and the last entry on this list is the only one that is not really about Mars at all. Number 1. 6 centimeters. Everything on this list was found in one of 3 ways. It was seen from orbit. It was found at the surface by something that landed. Or it arrived here on its own, as a rock knocked off Mars by an impact and collected, by chance, off a desert or an ice field. That is the entire evidentiary basis for what anyone knows about whether Mars was ever inhabited. And the surface of Mars is the worst possible place to look. Here is why, and it follows directly from the 6th entry on this list. Mars has no global magnetic field and effectively no atmosphere. Galactic cosmic rays, high-energy particles arriving from outside the solar system, reach the ground essentially unimpeded. On Earth, the magnetic field deflects most of them, and the atmosphere absorbs nearly all the rest, which is why we do not think about them. On Mars, there is nothing in the way. Those particles penetrate rock, and when they strike atoms in it, they produce showers of secondary particles that break chemical bonds. Complex organic molecules, long chains, rings, anything with structure, are steadily taken apart. Run the calculation, and the result is this. In the top meter or so of Martian material, organic molecules of the kind that would indicate biology are degraded beyond recognition over timescales of hundreds of millions of years. Most of the Martian surface has been sitting exposed for 3 billion years, which means that most of the surface of Mars has been sterilized of its own chemical history. Not of life, necessarily, of the record of life. The molecules that would tell you anything have been taken apart by particles arriving from other stars. To find an intact record, you have to go below that layer. The standard estimate is that you need to reach at least 2 meters into material the radiation cannot reach, and ideally into rock that was excavated or exposed recently enough that its clock started late. There is a partial way around the depth problem, and missions have used it. Where a recent impact or a fresh landslide has excavated material from below and thrown it onto the surface, that material's exposure clock started recently, and its exposure age can be measured directly from the isotopes cosmic rays produce in it. So, a rover can sometimes examine deep material without drilling for it, by finding the place where the planet did the digging. That is a real advantage, and it has been exploited. It is also a matter of luck rather than of design, and it does not put anybody's instrument where they want it. So, 2 meters. Now the numbers. Curiosity's drill bores about 6.5 centimeters into rock. That is the full stroke. When it drills a hole on Mars, the hole is the depth of a wine cork. Perseverance's coring bit takes cylinders roughly 6 centimeters long, which are then sealed into sample tubes. The Phoenix lander, working in loose polar soil rather than rock, scraped a trench about 18 centimeters deep, and that is how it found the ice. The Viking lander's scoops managed a little over 20 centimeters in 1976. InSight's self-hammering probe was designed to reach 5 meters. It got about 35 centimeters, and then the Martian soil refused to give it the friction it needed, and after 2 years of attempts, the team stopped trying. In 50 years of landed missions, across 6 successful rovers and half a dozen stationary landers, the deepest hole ever made on Mars is measured in tens of centimeters. The deepest drill core anyone has extracted from Martian rock is about the length of a finger. It is not that the missions were built carelessly. Drilling on another planet is genuinely difficult, and the machines have been remarkable. Curiosity's drill suffered a mechanical failure in its feed mechanism in 2016, and the team spent 2 years devising an entirely new technique, bracing the whole robotic arm against the rock and using it to provide the pressure the broken mechanism no longer could. That fix was designed and tested on Earth, uploaded across 100 million kilometers, and it worked. But a drill that reaches 6 centimeters, however elegantly repaired, still reaches 6 centimeters. The area is no better. Add up every square meter of Martian ground that has ever been examined at close range, imaged at microscope resolution, or analyzed by a contact instrument, or drilled by Sojourner, Spirit, Opportunity, Curiosity, Perseverance and Zhurong combined, and the total is comparable to a large parking lot. Mars has a surface area of about 145 million square kilometers. Because it has no oceans, that is dry land, all of it, very close to the combined land area of every continent on Earth. So, a parking lot on a planet with as much ground as Earth has, sampled to the depth of a finger. And nothing has come back. Not 1 gram of Martian material has ever been returned to Earth by a spacecraft. Everything in our laboratories arrived by accident, having been launched by an impact millions of years ago from a location nobody can identify, and having then lain in a desert or an ice sheet for thousands of years, collecting terrestrial contamination. Which brings us to the tubes. Since 2021, Perseverance has been drilling cores in Jezero crater and sealing them into titanium tubes, more than 24 of them, with a depot of spares cached at a site called Three Forks. They are the most carefully selected samples ever collected anywhere off this planet, chosen from an ancient river delta by a rover with instruments specifically designed to identify which rocks were worth keeping. One of them is called Sapphire Canyon. It was drilled in July 2024 from a rock named Shayava Falls in the Bright Angel Formation in Neretva Vallis, the river valley that once fed the lake in Jezero crater. The rock carries small dark spots the team called poppy seeds and larger markings they called leopard spots. Analysis showed those markings contain iron phosphates and iron sulfides in close association with organic carbon. That combination matters because of what it implies chemically. On Earth, patterns like that form when microorganisms drive reactions between organic material and iron-bearing minerals, extracting energy in the process. The mineral products are the exhaust. In September 2025, NASA announced it as a potential biosignature. The term has a formal definition, meaning a feature that might have a biological origin but requires further evidence before biology can be separated from the alternatives. It is not a claim of life. It is the strongest thing anyone has been permitted to say about a Martian sample. That tube is sitting on the surface of Mars right now. The instruments that could settle what those patterns are, the ones that measure the isotopic composition of individual molecules, resolve mineral textures at atomic scale, and test each possible formation pathway against the others, are all on Earth. They are the size of rooms. None of them can be flown. And Mars Sample Return, the mission that would bring the tubes home, has been repeatedly rescoped on cost grounds, with no confirmed return date. It is worth watching one of those cores being taken, because the whole of this entry is contained in it. The rover's arm extends over a pale slab of rock in an ancient river valley. The drill at the end of it begins to turn and then to press. Dust lifts and settles. The bit descends into the rock a millimeter at a time, and inside the hollow center of that bit, a cylinder of Mars is forming, a column of rock that has not been disturbed since it was laid down in water more than 3 billion years ago. The cylinder grows to about the length of a finger. Then the drill stops, because that is the whole of its reach. The core is withdrawn, transferred inside the rover's belly, photographed, sealed into a titanium tube, and the tube is closed. And then the rover drives a short distance, lowers the tube to the ground, and sets it down on the surface of Mars. It is still there. It has been lying on that plane through every Martian season since, in the dust, in the cold, at the bottom of a valley that was a river once, waiting for a spacecraft that does not yet exist. So the honest answer to the question this list has been asking is not yes, and it is not no. It is that we have never actually looked. We have photographed a planet exhaustively from above. We have driven a few dozen kilometers across it in total. We have scratched a handful of centimeters into it in 6 places, and from that we have drawn conclusions about 4.5 billion years of its history. The evidence for a previous civilization on Mars is absent. That is true, and it should be said clearly. But the evidence that would be required to rule one out is also absent, and for a reason that has nothing to do with anybody hiding anything. That evidence, if it exists, is 2 meters down under a radiation-scoured surface, or under a deposit the size of India, or 12 kilometers deep in saturated rock, or sealed inside a titanium tube on a plain in Jezero crater, waiting for a ride that has not been built. Remember what actually settled the face at Cydonia. Nobody was argued out of it. What settled it was a better camera, pointed at the same ground 3 times over 30 years, until the claim had nowhere left to stand. There is no better camera for the subsurface. There never will be. The only instrument that resolves what is under the ground is a drill, and the deepest one ever sent went 35 centimeters before it gave up. There is one on the way. The ExoMars rover Rosalind Franklin carries a drill designed to reach 2 meters, designed to that specification precisely because of the radiation depth, and built to deliver samples from below it into an onboard laboratory. Its launch has slipped repeatedly and is now planned for the end of this decade. When that drill turns, it will be the first time in the history of this species that anyone has looked in the only place where an answer could have survived. 20 entries, and this is where the list ends. Not on a discovery, but on a measurement of how little has been examined. 6 centimeters, on a world with the land area of every continent on Earth. The old surface is still there, under the dust, holding whatever it holds, and it has been patient for 3 billion years. It can wait a little longer for us to arrive properly. Sleep well and good night.